Uh-huh. Dear colleagues, please take your seats. I'm welcome all of you in Moscow State University. So it's the oldest university and largest university in Russia. So we have some repair works here on Moscow State University because next year we plan to celebrate 270 years old. So we prepare for this jubilee. Yeah. And I hope that our school, so we start to provide the schools, these kind of schools from 2019. So I think it's about five times. And I hope that this school, it will be fruitful and very interesting for you. So I want to take a floor to Vladimir Petrov. He is our supervisor of the lecture and practice part.
Thank you, Andrei. So I'm really glad to welcome all of you at this summer school on radiochemistry. Every time we have some a bit different topics. This time it is about radioactive waste management, and we invited experts from International Atomic Energy Agency, from the Rosatom company, company 12, one of the Rosatom companies. And also there will be specialists from company who are working on digital products for atomic energy enterprises and chemical enterprises in general. So I think that the knowledge that you will gain here will be useful for you, and it will be interesting. And Andrei, I think that we already have to put some numbers on before the name of the summer school, because it is already more than 10th our school on radiochemistry. Today we have 3 different schools every year. So it's summer school on radiochemistry, school on ecology, and winter school on radiochemistry. So at least 3 schools every year we have since 2019. So it's already a lot of different events that we organized, and more than 200 people already have been here. And I think that it was a great success for us and for that people. And today we have this topic on radioactive waste management. And my personal opinion that it is a very important topic, because if you work with radioactive materials, immediately you will produce radioactive waste in any actions. Either it is nuclear fuel cycle, or it medical applications, or it research work, or whatever. If you are working with radioactive materials, you will produce radioactive waste with different activity levels in different amounts, but anyway. And thus, this part, the management of radioactive waste, is a very essential part to work with. And I hope that I think many of you know some basics of radioactive waste management. What is it, and how to deal with that? But I hope that you will gain really some new knowledge and useful knowledge. So go into some technical details. I would like to first show, just a moment, a program. So you all of you have this program in color format, not in white and black. You see that every day we will start from 10 a.m. and we will finish approximately at 6 p.m. in the evening. So during the day you will have lectures, and at 2 days, on Wednesday and Friday, it will be 2 practical tasks regarding the immobilization of radioactive waste and separation of the radionuclides that are essential for radioactive waste management. And next week, it will be 3 days of lectures and closing remarks. Also today, we will be happy to hear from you just short presentations after the last coffee break, just for 1 hour. Short presentations about you. So, what are you working with? Where are you coming from? And some information about you. For us, it's always interesting to know what people are coming here. And also, uh, we have quite a plenty of coffee breaks. And lunch will be organized tour, let's say, to go to the lunch because we don't have a cafeteria here. So you will go outside of this building to another building to the chemistry department. Yes, to the main building of the Department of Chemistry. Um, what else? Maybe the most important information that we have toilets on the second and on the first floor. You will go down, and on the right hand, it will be two doors. First will be for males, and the second door for women's. So what else? I think from organizing point of view, that's it. And as usual, we have introductory tests, just small test. Don't worry about it. We don't really want to measure your personal knowledge, but some average knowledge of our participants. Yeah. So even if there will be a form that you will fill down your surname and name, don't be worried. So it will not go somewhere else. It's just information for us. We will have this introductory test now, and at the end, on the Tuesday evening, we will have the final testing of the participants. So again, just for us to see how good is the progress during the school or after the school. So I think I can finish with this introduction for now, and we will give you now this introductory test. Don't forget to put your name, and I think it will take 20 minutes to fill it. Okay. I think that we can start with a little shift. Maybe I will have a break in my lecture so that it will be not so exhausted. And yeah. So, and I would like to begin with some general introduction lecture about the basics of the nuclear fuel cycle, as far as we will speak mainly about the waste that are arranged from the nuclear fuel cycle enterprises. And in the beginning, just again, general information, a summary from different agencies, from the World Health Organization, from the other organizations. And first of all, it is this map of the, not the night sky, but night Earth that was made from the International Space Station. And you can see that, so this picture clearly shows us how unevenly distributed the production of electricity, of energy around the world. And if North America, Europe, some countries of Eastern Asia, they produces quite a lot of energy, quite a lot of electricity. But in Latin America, in African countries, in some Middle Asia countries, the production of electricity is not enough, maybe not sufficient. And this low access to the energy, it was estimated that more than 1 billion people has no access to energy, or as it called also energy poverty. That leads not only that people don't have, I don't know, sockets to plug in their computers, but also due to this energy poverty, there is no possibilities to use modern medical instruments, sophisticated medical instruments, and thus around 1 billion or even more than 1 billion people, they don't have a good health care due to the lack of the energy, to the lack of the access to the energy. Also, many or more than half of the population uses biomass fuels or biofuels. That means not green biofuel that is biodiesel or whatever, but mainly it is coal, oil, maybe some woods and others. These organic fuels, to burn them inside the houses to produce the heat, to make the houses warm, and thus the indoor air is highly polluted. And again, according to the World Health Organizations, more than 2 million deaths per year. So it is excess, it is extra deaths every year due to the contamination of the indoor air. So all of this leads to the understanding that we should change the structure of our energy production and make it lower, at least lower carbon, maybe not a low carbon, but we should try to decrease the percentage of the carbon-based fuel. And today, more than 70% of all the energy produced, it is produced from the fossil fuels. And according to the International Atomic Energy Agency, if we would like to reach the climate change goals, we have to change the structure of our energy production. And by the year
2050, more than 80% of all the electricity sources should be low carbon. But what are the low carbon sources? First of all, it is such renewable energies like hydropower, wind power, solar energy, and of course nuclear energy. These four types of energy production sources are the most cleanest because they produce the lowest amount of greenhouse gases. It is not totally zero because in these calculations, all the steps are included. That means that construction of the facility itself that requires a lot of cements, and the production of cements produces CO2, quite a lot of CO2 gases. So it is never zero regarding the CO2 emissions or other greenhouse gas emissions. But at least it is the lowest number among all the other sources. But also, what is even more interesting, that these four types of energy sources, they are also the safest sources. Here on the left side of this graph, it is numbers of the death rate from the accidents and air pollution caused by these sources of energy per 1 terawatt, if I remember correctly. Yeah, 1 terawatt hour annually from different sources of energy. And again, you can see that hydropower, nuclear energy, wind energy, and solar energy are the safest sources of energy. So together, these four types of energy they are believed to be, let's say, a green square. So this concept is at least used in Rosatom company. So these two main sources, nuclear energy and hydropower, it is really a huge production of energy, of electricity, and they're almost independent on any climate conditions, landscape conditions. Okay, hydropower depends on landscape, but once it is built and started to function, there is almost no deviations in its work. So it's stable production through the year of the electricity. And these two types, wind power and solar power, they both depends on the climate conditions, on the weather conditions, but they are important sources during the peak energy consumption. For example, during the day, when all the people go to the companies, to the plants, and you need more electricity to be produced for this. So these two types of energy can help to provide this additional energy during the day. Also, if we compare the capacity of energy production, we will see that the nuclear energy, at least, is the most concentrated type of energy source. And this is just an example that 26 cubic meters of natural gas produce the same amount of energy as 26 milliliters of the nuclear energy, because the nuclear forces, they are much more energetic than any chemical reactions or any chemical bonds. So it is very concentrated source of energy, nuclear energy, and thus it requires also the smallest area around all the other types of the energy production to produce the same amount of energy, of course. So if we have a nuclear power plant with the production more than, let's say, 1 gigawatt of energy, the area that is required for wind power plant will be 360 times more, and for solar panels it will be 75 times more area required to produce the same amount of energy. So in all this, from comparison of all these parameters, we can see that nuclear energy today is really one of the I would say greatest opportunity to produce clean and safe energy around the world, because again you can build a nuclear power plant almost everywhere. So you need only a source of water for cooling down your coolant, and that's it. So if you have a source of water, you can build your nuclear power plant everywhere. You can see it in the desert, you can see it in any area of Russia, even in the very north, where's this permafrost, so the always cold. Or you can see it in Japan, where a lot of seismic activity. So you can find a nuclear power plant in almost any conditions. And yeah, but again, nuclear energy, it's really a good source of energy. But what we have to prove to the community as specialists, that we can handle this energy safely. Yeah, and all the waste that are produced, we have to demonstrate that we can work with these materials safely, and that all these radioactive materials that are released from the nuclear power plants, from the other radiochemical facilities, all these radioactive matters, they are handled safely, and that we don't put this legacy, we don't leave it for the next generation. So today, it was not so in the past, because when 80 years ago, it was the main goal of all the radiochemical activities was to construct nuclear bombs, and nobody really cared about the ecology, about the environment, about future generations, because it was believed that if you don't have a nuclear bomb, there will be no future generations. Yeah? So in the USA, in UK, in Soviet Union, in France, the main idea, the main goal was to have materials to produce as many nuclear bombs as it possible. And of course, due to this very intensive running of these programs, a lot of radioactive materials were released in the environment. Yeah, and all these contaminated areas were left for the future generations, and for someday when somebody will take care of all this contaminated area. And today is this day. Today we have to work with all these legacy sites, with legacy facilities, and also not only to work with the legacy, but also we have to provide technology that will not leave all the same legacy for our future generations. So today, the main idea, if we are talking about new facilities, about new plants, that there will be no postponed decisions, that we will take care about all the radioactive materials that are produced today, and yeah, that there will be no problem for future generations. And this year, just months ago, we celebrated the 70th anniversary of the industrial nuclear energy production. So the first real industrial nuclear power plant was commissioned in 1954, not far away from Moscow, in Obninsk. So it's around 100 kilometers from here. And it was if we compare it to the modern reactors, of course, it is very small. So it was only 5 megawatt reactor, but it was a really important point when this nuclear energy produces the electricity that were connected to this electrical grid to the city of Obninsk. So this nuclear reactor produced energy for the city, not for research institute, not for some military purposes. It was designed and constructed specifically to produce electricity for citizens, for general population. And today we are already speaking about the generation 4 reactors. There are different concepts of these reactors. Fast neutron, mainly fast neutron reactors with different coolant, sodium coolant, lead coolant, or high temperature gas reactors, or even molten salt reactors. But the idea about this generation 4, it's not only the maximum utilization of the fissile materials, but also to provide the, let's say, absolute safety as declared, but we understand that there is no absolute safety in any areas. Even when you go outside on the street, there is always a risk that something will happen. The same is in nuclear reactors, in handling of radioactive materials. There is always some risk that something will happen, but today this risk is minimum, is very, very low. And coming back to the nuclear energy and energy production, when we are talking about the production of energy, of course, many people firstly think about the nuclear power plant. But actually, nuclear power plant is just one of the steps in the so-called nuclear fuel cycle that started from the very beginning of the mining of uranium, or extraction of uranium, refining uranium, then conversion to uranium hexafluoride for the enrichment, because modern nuclear reactors, they are mainly, more than 90% of all nuclear reactors, industrial nuclear reactors, work on enriched uranium. That means that the fuel has to contain more uranium-235 than it is contained in natural uranium. So in the form of uranium hexafluoride, uranium is enriched by the isotope uranium-235, and this uranium hexafluoride converted to uranium dioxide. Then the fuel is fabricated, this fuel assemblies, and only after this step we come into the nuclear power plant. Then fuel for several months working in the nuclear reactor, and then it's not a finish. After spending some times in nuclear reactor, nuclear fuel goes to the special pools. The spent nuclear fuel stored for several years for cooling down, to make all the short-lived radionuclides to decay. And then there are two ways. Either it is so-called open nuclear fuel cycle, when the spent nuclear fuel, without any processing, the spent nuclear fuel is placed in the special containers, and it goes directly to the geological disposal. Today there is no Iranian geological disposal. Actually, only in USA. Actually, they have this waste isolation pilot plant. In the name of this facility, it is written pilot plant. So formally, it is not a final disposal, not a final repository. But actually, they put in all the spent nuclear fuel there, and I think they will take the spent nuclear fuel out. So actually, even informally, it is the first geological disposal. But yeah, let's say not really officially. Official geological disposal first will be in either in Finland or in Sweden. There is still no information who will be first, but anyway, in this open nuclear fuel cycle, the management of spent nuclear fuel is very simple. You do nothing with this, only store for some time, put in canister, and put in the final repository. But in this way, all the valuable components of spent nuclear fuel will be buried underground. But the closed nuclear fuel cycle means that we process the spent nuclear fuel, we extract valuable components. That means that components that can still be used as components of the fresh nuclear fuel. And this fresh nuclear fuel fabricated from the spent nuclear fuel again used in the nuclear power plant. So in this way, of course, you use more intensive all the fissile materials, but at this point you have to build this reprocessing plant, and you have to deal with all the radioactive waste arised from this reprocessing plant. So from the economical point of view, both open and closed nuclear fuel cycle today have the same values, the same cost of the production of the electricity. But with the increasing price of the uranium product, natural uranium product, I think that the closed nuclear fuel cycle will be cheaper and cheaper. So, and before going to the sources of radioactive waste, we should answer what are the radioactive waste. Yeah. So first of all, as far as it radioactive, that means that it is material that contains or contaminated with the radionuclides. The second part of this term is waste. So that means that there is no further use, at least with current technology. Yeah? So maybe in the future, after 50 years, these materials can be used. But today, we don't have technologies that allow us to use these materials in any application. And there is one central part that is missing, very important part. I will explain it. So, first part, that material contains radionuclides. It really means nothing, because all the materials around us and even us, we contain radionuclides. Yeah, so radionuclides are everywhere. So to say that this material is radioactive waste or some material that needs to handle in specific way, the content of the radionuclides should be higher or greater than the clearance levels that are established by the government. So in different countries, there are different levels. They are more or less the same from country to country. There are some deviations according to the local laws, but they are more or less the same. So, and if your material has radionuclides concentrations above this clearance level, that means that you should handle these materials in some specific way. That is very important, because again, radionuclides are everywhere, and if you don't put this very important part in your definition, that means that every material will be radioactive waste or radioactive material. Okay. So, and let's go from the different steps of the nuclear fuel cycle. Okay, let's go. just few slides, and then we can have a break. So let's start with the mining of the uranium ore. There are three main types of the uranium ore mining. It is either carriers or mines or underground leaching. So underground leaching is, I would say, the best way from the ecological point of view, because in this case, you have just several wells through which you put your leaching solution. It is either carbonate, sodium carbonate solutions, or it is sulfuric acid. It really depends on the geological conditions, which type of the solution you should put inside. If it is, for example, carbonate minerals around your uranium ore deposit, that means you cannot put some acid inside. Otherwise, you will produce a lot of CO2 and precipitation of calcium sulfate and many other problems. So in this way, you should use sodium carbonates, for example. So it really depends on the geological conditions. You can choose which leaching solution you will use. But also, this ore itself should be so the solution should have a possibility to go through this ore. So it should be permeable. If it is like a solid rock, you cannot use leaching, because no solution will go through the solid rock. So this is very good, underground leaching, very good for ecology, because when you finish your extraction, all the ore is depleted. You just put out these wells, and in 10-15 years, there is no sign that there was something industrial. So all the environment remediate itself very quickly. So, and there is no huge construction on the ground. But in these cases, in the case of carriers or mines, you put all the ore on the ground. You construct these heaps, and you put some acid on the top of these hills, and you collect the acid solution that goes through these hills or heaps. And you collect it, and it contains uranium, of course, with some other metals. That's why you have to purify it later. But this solution, mainly it is sulfuric acid solution, goes further for the extraction process, extraction with the most used commercial extractant in our industry, TBP, tributyl phosphate. In kerosene, you extract uranium, you back extract uranium, and you precipitate uranium as either as ammonium diuranate or sodium carbonate uranate, or some other salts. So this is the main general scheme of this technology. And of course, in these two types of the mining, you produce a lot of these byproducts, a lot of these tails, and very huge impact on the environment. So you can see how looks these tails after the extraction of uranium. And of course, these tails, they contain concentrated natural radionuclides that are the decay product of the uranium. So it's mainly radium-226 and its decay products. In these areas, in these tailings areas, due to the concentrated radium content, there is a lot of radon production, and radon, it's a noble gas that goes easily from any material and goes to the air, and also with the underground water flows, it goes to the let's say villages or households, and it goes to the people, to the population, and irradiate population, extra irradiation of the population. So these tailings today should be removed, and luckily there are a lot of big programs in different countries that are dealing with these tailings, and they remediate, the government remediate these territories, and they are removing all these tailings, and it is good. So one of the example of the radioactive waste produced from the natural materials in the first steps of the nuclear fuel cycle. Then, after extraction and purification of uranium, there are several steps before production of uranium hexafluoride. Of course, at every of this stage, you produce either solutions or solid materials, filters, or whatever containing this uranium, containing some, again, natural radionuclides, and you produce a lot of waste that contain uranium. So this uranium hexafluoride before enrichment and after enrichment is stored on the daylight surface in these barrels. And the problem with this material that it is not really highly radioactive. Of course, it is uranium, but the radioactivity is not very high. The main problem that is that this product is chemically dangerous, because due to the interaction with water, just with moisture in air, uranium hexafluoride can hydrolyze and produce a lot of hydrofluoric acid. And it was such accidents, unfortunately not on the daylight surface, but inside the facility, when one of the barrel was not good sealed, and this uranium hexafluoride contacted with air, and a lot of hydrofluoric acid was produced inside the room, and people died just because of the chemical intoxication and chemical damage of their lungs. So this product mainly dangerous due to the chemical reactions. And when we produce uranium hexafluoride, it is very good material for the enrichment of the uranium. So natural uranium contains approximately 0.72% of uranium-235. And as I mentioned before, uranium-235 is the main uranium isotope that is required for most of the modern nuclear reactors to produce energy. And to do so, we need to enrich this uranium mainly for fuel. For modern reactors, it is from 2 to 5% for uranium-235, but in some applications for research reactors or for example, small modular reactors, we need a higher enrichment of the uranium. And as far as we enrich part of the uranium, another part is depleted with uranium-235. There are two main methods that are used today. It is either gas diffusion method that is used in USA, or gas centrifuges that are used in other countries, including Russia. Why uranium hexafluoride is so good? First of all, it has low sublimation temperature, so this material goes to the gaseous phase without going through the liquid phase at a very low temperature, so from solid to gas only at 56 Celsius degrees. And from another point of view, fluorine is very good, because natural fluorine has only one isotope, and so it makes it easier to separate uranium-235 in form of hexafluoride and uranium-238. For example, if it would be oxide, natural oxygen has at least three stable isotopes, so you will have a range of different combinations of the masses, uranium-235 and oxygen 16, 17, 18. So it will be really difficult to separate all these masses. But with fluorine, it is only one natural stable isotope, and it makes it much easier. So it's a really unique compound for enrichment. An enrichment facility, at least in Russia, it's really huge facilities. There are 100 meters long corridors with these gaseous centrifuges to produce the highly enriched uranium. And unfortunately, due to different accidents in production, maybe some spill over of the materials or whatever, the soil around this production contain some higher amount, higher than natural amount of uranium. So after the decommissioning of this facility, it will be required to clean up this territory. And today we have mainly, again, in more than 90% of all nuclear reactors, it is oxide fuel. Yeah, so we have to convert uranium hexafluoride to uranium dioxide. And some of the reactors can use also so-called MOX fuel. So it's mixed oxide of plutonium and uranium. And 2 years ago, in 2022, it was also like a milestone in nuclear energy when in Russia, in the reactor BN800, all the active zone of the reactor was replaced by the MOX fuel. So it was first time in history of these reactors when the full active zone was filled with the MOX fuel. So it was initially designed to use MOX fuel in such type of the reactors, but in the beginning it was a decision to put first only uranium dioxide fuel, and then step by step they replace assemblies with uranium dioxide with the MOX fuel. And in 2022, all the active zone was filled with the MOX fuel. So one of the another iconic event, I would say, in our nuclear energy technologies. And today also there is a need to produce nitride fuel because it is more dense fuel. So if you have more dense material, you have again more concentrated source of energy. And this type of fuel will be used in new type of the reactors, fast neutron reactors with the lead coolant. I will show it a bit later. And yeah, there are some another very complex fuels like composite fuel, this, for example, TRISO fuel, where you have uranium siliciide covered with the pure carbon, silicon carbide, and some graphite. So it's very complex fuel for reprocessing later, and liquid or molten salt reactors that today is under construction as well. So it will be fluoride salts, molten salts, and the reprocessing of such materials will be also quite challenging. So, but when we produce this fuel, there is always some fuel pellets with defects. There is some old fuel that was not used or sent to the to the nuclear power plant. And all these materials should be also reprocessed, so it should be dissolved, purified, and refabricated. And during all this operation, we produce liquid radioactive waste of different, sometimes very complex compositions. So even at this stage, when it seems that we are working with the solid material, so just uranium dioxide, not very radioactive, but still we produce, due to the different technological processes, radioactive waste. And yeah, after all these steps, finally, we come up to the nuclear power plant. We put our fuel in the nuclear reactor. We don't look today precisely in the details of the reactor. It's just, let's say, heating of the coolant and transfer of this heat to the second circle where water generate vapor or steam, and steam rotate turbine and produce electricity. So it's very simple or general scheme of the production electricity in nuclear power plant. Again, there are much more details inside, but we don't go there. But what is important, again, in the beginning, uranium fuel contains only two elements, uranium and oxygen. But after working in the nuclear reactor, due to the fission, due to the activation of the construction materials of the nuclear fuel itself, now there are more than 50 other elements generated in the spent nuclear fuel. Of course, all these elements have different chemical nature. It is alkaline metals, alkaline earth metals. It is noble metals. It is gaseous products. So the composition, chemical composition of the fuel changes a lot, but not only the chemical composition, but also the physical properties of this fuel changes a lot. That's why after some certain time, we have to replace spent nuclear fuel. It is not due to the problem that all the uranium is burned up, but it is due to the problem that the properties of the nuclear fuel changed so much that it can no longer be used in the reactors due to the thermal properties, due to the presence of the neutron poisons and other reasons. So you can see this. So if you will see this type of the grains of the uranium dioxide with all these bubbles, let's say, you can definitely say that it is not a fresh fuel, but a spent fuel, because these bubbles, it is a sign of formation of the gaseous products inside the nuclear fuel. So that means that this fuel worked a lot in the nuclear reactor. So it's really simple to say that it is spent nuclear fuel and not the fresh one. So I think that we can stop here to take a break, a short break, like 10-15 minutes, and we will continue. Okay. Okay, let's continue with our spent fuel. Here you can see that after the reactor, there is only 3% of the products that cannot be longer used. All the other, let's say 97%, can be recycled and used again as a fresh nuclear fuel or in some other applications. So is the spent nuclear fuel waste or not? If we are talking about the open nuclear fuel cycle, then it is waste, because we don't process it and put directly in the repository. But in closed nuclear fuel cycle, at least in Russia, by law, spent nuclear fuel is not a radioactive waste. So it's a material, a valuable material, and a source of the fissile materials, so uranium and plutonium, and some other elements. And today we are speaking about so-called dual component nuclear energy. Two components. It is a neutron reactor and a thermal neutron reactor. So these two types of the reactors, they work together. In thermal neutron reactors, we used either fresh uranium fuel or some part of the MOX fuel. So in another reactor. After working in these reactors, nuclear fuel contains some plutonium. It contains still a lot of uranium. And this fuel, spent nuclear fuel, goes to the reprocessing plant. The uranium, again, used for production of the fuel for these thermal neutron reactors. But plutonium, it is not very good plutonium because contains some even isotopes that cannot be fissile in these types of the reactors. So this plutonium goes to the production of the MOX fuel for fast neutron reactor. There it goes, and due to some physics, neutron physics, plutonium isotope parameters, isotopic composition becomes better, let's say. So it becomes high fissile plutonium. And this high fissile plutonium can be used, as I mentioned before, in MOX fuel for thermal neutron reactors. And again, it goes to reprocessing, and part of the plutonium, this plutonium from thermal neutron reactors goes as a fuel for fast neutron reactors, and this plutonium from fast neutron reactors goes as a part of the fuel for thermal neutron reactors. So these steps allow to use very efficiently all the source of this fissile material, starting from the uranium, then plutonium that accumulated in thermal neutron reactors, and then improved, let's say, plutonium in the fast neutron reactors. So today, it is the main strategy of not only Russian energy system, but also, for example, Chinese system. It's more or less the same, using two components in the energetic system. And it's like a philosophical point of view that the back end stages of thermal neutron reactors, so it's the reprocessing of spent nuclear fuel from these reactors, now become the starting point for the fast neutron reactors, so initial stages for fast neutron reactors. So it's really interesting situation. But to do this, to make it possible to use this dual component nuclear energy, a lot of technologies, a lot of processes have to be developed. And first of all, it is the production or fabrication of the MOX fuel. And for next generation reactors, it is not oxide fuel, but nitride fuel. But also to make possible to fabricate the fresh nuclear fuel, it is important to have technologies for separation of all these elements from the nuclear fuel. So in the fuel, in the fresh nuclear fuel, we can use uranium, plutonium, americium, and neptunium. All other components should be separated and stored for some time, may be used in some technologies. For example, cesium-137 or strontium-19 can be used in different applications, like source of gamma quanta for some application, or as a source for small batteries, let's say, based on the radioactive decay of the strontium. So what the other benefits of spent nuclear fuel reprocessing? So first of all, we reuse many times these fissile materials, uranium, plutonium, and other actinides. But also, if we will look on this potential radiotoxicity of the spent nuclear fuel, this is the starting point. So today, spent nuclear fuel is the most dangerous material, most hazardous material on our planet, the fresh spent nuclear fuel. But due to the radioactive decay, this radiotoxicity goes down, goes to the level of natural uranium ore. So it's not so toxic, yeah, so it's natural uranium ore. But if we do nothing with spent nuclear fuel, this total radiotoxicity will reach the level of natural uranium ore only after, let's say, 100,000 years. So very long time to wait, because the whole history of humankind is approximately 100,000 years. Yeah, so very long time to wait. So that means if we bury all this spent nuclear fuel without reprocessing, that means that we should provide or confirm that our repository will be safe for such a long period of time. So it's really difficult technology, difficult project, and really difficult to confirm it. But imagine if we delete or extract all these long-lived radionuclides. First of all, plutonium and americium, partly curium. You can see that in this case, only fission products will be left in this material. And already after 300 years, this decay of the fission, due to the decay of the fission products, this material will reach the level of natural uranium ore. So 100,000 years and 300 years. It's a big difference, really huge difference.
Yeah, for 300 years, we don't need even use deep underground repository. For 300 years, for fission products, we can use subsurface repositories, and it makes it much cheaper to construct. So here many benefits from the reprocessing of spent nuclear fuel. First of all, the more intensive use of the fissile materials, then decrease the time of the potential hazard of this radioactive materials. And third, it is cheaper underground repositories for only fission products, excluding all the long-lived actinides. But if we remove these long-lived actinides from our material, it doesn't mean that they are disappeared. Yeah, so we should do something with these long-lived radionuclides, and there is an answer to this. It is transportation in the special reactors, in the fast neutron reactors, and we already have a great experience in working with the fast neutron reactors that are sodium cooled reactors. And nowadays, right now, the new reactor called Brest reactor with the lead coolant is under construction already in Siberia near the Tomsk in the city of Seversk. And so it is a demonstration reactor, so it's not very huge. It's only 300 megawatt of energy production, but it is important milestone again in the development of nuclear energy. First of all, this reactor can utilize not only uranium and plutonium, but also minor actinides like americium and neptunium. Maybe it will be possible also to utilize technetium and iodine, but it is for future investigation. But americium and neptunium certainly can be utilized in this type of the reactor. And that is most important, that this reactor, Brest reactor, will be a part of the complex energy facility that is called energy how it's called demonstration energy complex. Experimental demonstration energy complex. So what is the idea? That on the one side, it will be the fabrication of the fuel for the reactor. It will be a reactor that will utilize the fuel. It will be a reprocessing of this spent nuclear fuel from this reactor, and the facilities for the immobilization of radioactive waste to make them in the final form for future repository. So all on one site. So all the closed nuclear fuel cycle on only one site. And it will be in pilot scale. Again, this reactor will be only 300 megawatt, and it will produce about 10 tons of spent nuclear fuel per year. So all the facilities, they're designed to deal with this amount of the spent nuclear fuel. But nowadays, it is already under development. The industrial scale energy complex that will consist of two reactors, lead coolant reactors, with the energy production of 1,200 megawatts, two reactors, and all these facilities for fabricating and reprocessing of spent nuclear fuel, fabricating of fresh fuel, reprocessing spent nuclear fuel, and immobilization of radioactive waste. So it's a really a promising future, and we will see how it will work. And again, I will repeat that this reactor is already under construction. So hopefully in 10 years, maybe it will be commissioned. And if we reprocess all this waste, if we extract all these long-lived radionuclides, another benefit is that we will decrease the volume of the high-level waste. So it is just an example of the volume of high-level waste generated by using nuclear energy with the modern technology, with the Purix process. And the energy generated for one family in a lifetime. So it's 4 persons for 70 years of the lifetime. So and you will see, you can see that it is already quite a small volume of the waste, because every day I think we produce much more common waste like plastic or paper or whatever. And this is for 4 persons in 70 years of generating of energy, this small amount of high-level radioactive waste. But if we extract all these long-lived radionuclides and utilize them, the amount will be even lower, and the volume will be much, much smaller. So this is another benefit of the reprocessing and utilization, transmutation of the long-lived radionuclides. But how to separate all these components of the spent nuclear fuel? I mentioned that there are around 50 different chemical components in the spent nuclear fuel. And to do so, the main technological process is a liquid-liquid extraction. So after the dissolution of the spent nuclear fuel, we use these properties of two immiscible liquid to extract one of the components in the organic phase, and then back extract it to the aqueous phase. And to separate actinides between each other, we can use redox reactions because there are plenty of stable oxidation state of different actinides. So the general scheme, since the, I don't know, 60s, I think, there is a Purex process that is used all over the world, in France, in UK, in Russia. So it can be advanced Purex, modified Purex, but the general scheme is more or less the same. After dissolution of the fuel in nitric acid, there is extraction by tributyl phosphate in kerosene or other diluent. In this case, uranium and plutonium are extracted. There can be also extraction of neptunium and some other activation and fission products, but the main extraction is for uranium and plutonium. Then, after separation of this organic phase, it is stripped with the some reducing agent, either it is iron 2 or some small organic molecules, or uranium 4 or some other reducing agents. What is the purpose? The purpose is to reduce plutonium 4 to plutonium 3. In this oxidation state, plutonium 3 is no longer extracted, so it goes to the aqueous phase and uranium stays in organic phase. And later uranium also back extract to the aqueous phase simply by diluted nitric acid. So it looks very simple, but of course in technological process there are plenty of difficulties, let's say, precipitation of some components containing zirconium, molybdenum. There is technetium that present everywhere, and some other difficulties. But at least today, technology can work with all these elements. And today after this separation, we can produce pure uranium oxide and plutonium oxide, mix them later to produce MOX oxide fuel and some other processes. And to separate all the other components today, there are plenty of new technologies with different names under development or under pilot scale investigation already. And it just very, very small list of the ligands of different structures, maybe some classes of different extractants that are developed today, and many more under investigation. And what is the purpose of all these extractants is to separate high-level waste, to fractionate them, because except uranium, plutonium, americium, neptunium, And there are other components like cesium and strontium that I mentioned before that can be used in some applications. Or there are noble metals that can be used as catalyst also in some applications. For oil industry, for example, and some other components like technetium or iodine that can be also separated for further transmutation or whatever. So a lot of different processes that are aimed to separate individually some components in the pure state. But of course, as far as we use nitric acid, organic solutions, we produce a lot of liquid waste. And as I mentioned in the beginning, that in the 40s, 50s, even 60 years, there was no a big concern about the environment, and many radioactive liquid waste, they were released just in natural reservoirs, in rivers, in ponds, and even in USA, for example, they produce these tanks that are already 70 years old, but still there is no solution for the waste that are located in these tanks. And these tanks, they were constructed, they were designed for only for 50 years, but it's already more than 70 years. So these tanks are already corroded, and some part of the radioactive waste goes to the environment. And it's really a bad situation because in this case, there are alkaline liquid radioactive waste with a lot of suspensions, with a lot of sludges on the bottom, and actually nobody knows what to do with these very complex materials. So a lot of problems that we have today and that we have to solve. And when we are talking about the disposal, we always talking about this multi-barrier system or multi-barrier concept, where the central part of the system for protecting ourselves from the radioactive waste. It is radioactive waste in some of the metrics. Here it's vitrified metrics, but tomorrow we will talk about different matrices for radioactive waste. These metrics with radioactive waste placed in some overpack, in canister, in some overpack, and then it located in some underground facility, and the space between the natural rocks and this canister also filled with some buffer material that should avoid penetration of water to the canister, or if the canister will fall down, this material should sorb or prevent the release of the radionuclides outside the disposal. And of course, several hundred meters of the natural system, natural barriers, rock, should prevent the transport of radionuclides to the environment. So it's really like a Russian doll, multi-barrier system with a lot of different shells around radioactive waste. So if we will go back to our nuclear fuel cycle, and if we will ask ourselves where are the radioactive waste, where are they produced, the answer will be at every stage. As I mentioned before, that when we are working with radioactive material, sooner or later we will produce radioactive waste. And as part of all the nuclear facilities life cycle, it is not only operation when we create radioactive waste, but also the final stage of any of nuclear facility is the decommissioning. And during decommissioning, of course, we produce also radioactive waste. So again, radioactive waste, they are produced not only during the operation of our facility, of our radioactive materials, but also during decommissioning when we already shut down our facility, but still we produce some kind of radioactive waste. And so decommissioning, by the definition, is this actions taken to allow to remove of some or all regulatory control from a nuclear or radiological facility. And there are three main technological steps. And again, at every of these steps, we produce radioactive waste, which we handle differently, but still we have to remember that decommissioning is not only to remove the facility from this site, but also to produce a lot of radioactive waste. And it is not only a nuclear fuel cycle facility, of course, that produce radioactive waste. It's many, many other areas that use radionuclides, either in medical care or industrial sources of X-rays that often use these iridium isotopes or other isotopes that produce X-rays. Research reactors or research facilities where we work a lot with radioactive materials. Food and agriculture that use sources of gamma radiation for different application for sterilization of the products, for example, or for, again, investigation of the mutation of the materials, plants or animals under irradiation. I already mentioned this naturally occurring radioactive matter waste. They are arised not only from the mining of uranium, but also during mining of other natural minerals like phosphates or during the mining of gas and oil. There are also some norm waste that are produced. And of course, accidents, if there are any, also produce some unusual type of waste. But good point of radioactive waste, it is a radioactive decay. So all the radioactive materials are decaying, so there is no stable radioactive materials here. So sooner or later, their activity decreased. So that means that after some time, the toxicity or danger or hazard of these materials will decrease just by natural radioactive law. And again, this relative toxicity of different materials, and spent nuclear fuel is the most dangerous materials. But after some time, even without reprocessing, the spent nuclear fuel, its radiotoxicity decreased to the natural levels, even uranium ore levels. But you can see that some common chemical elements like chromium or mercury or cadmium or other materials, they are stable. So their toxicity will last forever, except the toxicity of radioactive materials. So it is, of course, not the point that we all should produce radioactive waste, but we should remember this graph when we are talking about the disposal, for example, of radioactive waste, because this graph means that we should confirm the safety of our materials only for some certain time. We don't need to construct a repository that will be safe forever. Yeah, only for some certain period of time, 300 years, 1,000 years, maybe 10,000 years, but it's some certain period of time. And then there will be no longer danger from this material. So some brief conclusions that nuclear energy today, it's important. It's clean and safest, the cleanest and safest source of energy. We remember that nuclear fuel cycle, it's not only the nuclear power plant itself, it's all the stages from mining of uranium ore, extraction of uranium, production of fuel, and then handling of spent nuclear fuel, and all the radioactive waste that are a result of the any activity with the radioactive materials. Um, at the final stage of any facility, there is decommissioning that is also source of radioactive waste, and reprocessing or fractionation of nuclear waste or radioactive waste can significantly reduce not only the activity but also the time of danger of this material, and it can result it in very good economical profit. And when we're talking about the storage and disposal of radioactive waste, we are always talking about the multi-barrier system, about multi-barrier concept. So, and yeah, the final point that the hazard from the radioactive waste is finite. So, thank you for your attention. It is my last slide for this presentation. If you have any questions, I will try to answer them. Not. If there are no questions, then we can wait a couple of minutes for Olga, who will guide you to the lunch, to the cafeteria. Okay, thank you. So, dear participants, we have a special lady here. Her name is Anna, and she has this special tickets for the lunch. So please take one. I did, yeah. So it's for today lunch, and go downstairs. Wait for a couple of minutes for everybody. Okay. So take one ticket.
Wakatongotiye nawo iyi meeting yakurasha iyi.
How? Cause I can't explain. It's nothing short of a miracle. I'm here.
Михаил Иванович, слышно нас сейчас? Добрый день.
Владимир, если мне, то добрый день.
Да, вам, Михаил Иванович.
Спасибо. Вы обязательно это дайте мне возможность раздать экран. Пока у меня такой возможности нет.
Сейчас. А сейчас не появилось?
Так, сейчас посмотрю. Появилось, спасибо.
О, отлично.
Так, посмотрите, у вас он появился?
Да, все видно, отлично.
Отлично, спасибо.
У нас есть 2 минутки и начнем.
Хорошо.
Okay, I think we can continue with our next lecture, and the next presenter is a very well-known expert in the field of radioactive waste management, the expert of International Atomic Energy Agency, Professor Michael Ojovan. So, Professor Ojovan, the floor is yours.
Thank you, Vladimir. Dear participants, welcome after the break. The regulatory part, which was offered to me, has two actually slots. So the first one is now, and another one will be tomorrow in the morning. So hopefully that you see the screen, and let me introduce a couple of words about myself. So my name is Michael Ojovan. The lecture is about the basics of nuclear waste management, and I'm focused on regulations. So both today and tomorrow are the things related to regulations of activities in the area of nuclear waste management. From the beginning, you know that the radioactive waste and nuclear waste, these are synonymous. So it's the same meaning. It's no difference. It's radioactive waste or nuclear waste, because the radiation comes from the nucleus. So I'm affiliated with the School of Chemical Materials and Biological Engineering in the University of Sheffield, United Kingdom. I was affiliated, and recently I'm also working, like now I'm teaching to you, in the Department of Radiochemistry of Lomonosov Moscow State University. My immediate past, I worked in International Atomic Energy Agency in the headquarters in Vienna from 2011 to 2018 as a staff member in the waste technology section there. That's Department of Nuclear Energy. And also as a professor in the Department of Materials in the Imperial College London. But my contract with Imperial ended, so from April, I'm in the University of Sheffield, United Kingdom. So I put, because of that, these symbols of International Atomic Energy Agency and Imperial College London. And greetings to everyone, participants in the International Summer School on Radiochemistry. In the middle here, I put also the indication that I'm leading as a editor-in-chief or chief editor, the most influential journal of nuclear industry, namely industry. So rather focused on industrial applications of nuclear energy rather than research. Also comprising. The journal is called Science and Technology of Nuclear Installations. And initially it belonged to Hindavi, but from this year it is a part of Wiley publisher, Wiley publisher. So that's these are my affiliations. So this 1 hour slot, let's move to the business of basics, regulatory, let's say, basics of nuclear waste management. So I'll put here the clock not to extend my time. So the 4 sections of my today lecture for you. And important introductory, then I will actually enter into these international regulations, which will be continued to tomorrow in the morning. Today, I will cover the safety principles, the most important things as the basis of all international regulations in the management of radioactive waste or nuclear waste. Dear participants, you see here, it's not advertising. It is just to make you informed. So this is the cover of the 3rd edition of a book, of a monograph, which is co-authored by myself, by Professor Billy from Imperial College London, and by Professor Kalmykov, who is from the Radiochemistry Department of Moscow State University, Lomonosov Moscow State University. So this is already the 3rd edition. So first it was published in 2005, so 2005. And that was the basic manual, was intended and created as a basic manual for the students who attended the Nuclear Technology Education Consortium of United Kingdom. So this consortium is physically located. So I'm myself in Sheffield. Sheffield is a big city where the Industrial Revolution started in the world. So it's actually well known for stainless steel, Bessemer processes, metallurgy, etc., but also for glass science. But the Nuclear Technology Education Consortium physically is located in Manchester. So most of you perhaps you know because of Manchester United, soccer, football. So just finished the European Championship with the Spain, who beat unfortunately the England for me, but fortunately for the football because they played much better. So that's in Manchester. So Nuclear Technology Education Consortium, it is giving education for all areas of the use of nuclear energy. And the module on nuclear waste was actually my module that I physically taught before I moved to Vienna to headquarters of IAEA in Vienna. So based on lectures and so on, we created and published the first edition in 2005, so 2005, this manual. So if you are more interested, you need the references, you want to know more about all these activities in nuclear waste, then this is a good reference. So it's well quoted, so it's known for researchers, not just for students. And by the way, the lecture is available. I submitted it to Elena, who is organizing the course. So maybe Putyatin also, Andrei, who opened the course also. So the file, I mean, this one has the link. But nowadays, if you know the title via Google, you can find everything, the names, organizations, etc., etc. So it's for your information. There is the link is also here. So let's move to the regulations, to basics of nuclear waste management. So I'm starting with the background information. Although a little was given today in the introductory lecture of Professor Petrov. So you already got from him things like he also paid attention to the definition of what is the nuclear waste or radioactive waste, because I noted these are the same synonym of the same material, radioactive waste or nuclear waste. But I took this, you see it's copy-paste. A couple of slides here are created using copy-paste from this book. And this book, you see the cover of it. So this is IAEA safety standard. And in the past, this standard was before publication of this version, published in 2014 by the IAEA and other organizations here. Well, all the people like myself, older a little bit, it was called basic safety standard. So if you work in the area of utilization, nuclear medicine, education, everything, then this is a kind of Bible, a kind of a handbook that you can find definitions, numerical data, recommendations, all things. And some of the tables I will show you in the next slides of this lecture as well, taken from here. So it's basic safety standard. Everybody knew this book as a basic safety standard. So in this basic safety standard, there are definitions. And you see here the definition that Professor Petrov already paid attention to it in the introductory lecture. So what is the radioactive waste? What is the radioactive waste? So first of all is the waste. If it is the waste, nobody needs it. It's like trash, it is like garbage. So we are getting rid of it. So throwing it, collecting in a bin and so on. But historically, during the development of civilization, initially, humans, we were throwing everything like animals do, and the nature digested the waste that humans as species were producing. But after, particularly when the Industrial Revolution occurred, we are producing so much waste that the nature cannot cope. So now it's not just, throw it and forget. We are collecting this waste. We are paying much attention to the waste that let's say 100 years ago or 150 years ago. So nowadays it's an industry of waste management. And by the way, the nuclear sector was the first industry to take care as a dedicated part of the industry, which is nuclear waste management. So definition. So I have here the pointer. So you see here, maybe from far from the auditorium, you cannot read all the text here, but so the radioactive waste, and a little bit strangely, the definition. So this definition is then taken to legal documents, to taken one-to-one in kind of agreements and other standards, etc., etc. So it's copy paste from there, because this is a very important one. But it starts with the statement that for legal and regulatory purposes, the material which no further use is foreseen. So if no further use is waste. And it starts that for legal and regulatory purposes. And Professor Petrov emphasized that. The waste, if you take any waste, some pencil that I don't need it, throw some papers, all kind of the trash. If you take samples from there, we say we take environmental sample for analysis, water from the environment, etc. We go to a laboratory, and then we start to identify that there are some traces of radionuclides there. So without this start of this definition that for legal and regulatory purposes, all kind of the waste would be radioactive waste. And then end of activity of industries, because radioactive waste management is carried out under strict guidance and regulatory documents. And this lecture and tomorrow one will give you the basis of these regulations. And it's a very expensive, time-consuming, resource-consuming activity. And if we will declare, and we have all the reasons to do that, the ash, which is produced after incineration of the coal, which has a lot of thorium, uranium there, radioactive materials are there. But this ash is not declared radioactive waste, it's just waste. Next week, not this, I have a lecture on so-called norm waste. Norm is abbreviation from naturally occurring radioactive materials. Naturally occurring radioactive materials. And we will speak about the ash a little bit. So the definition of radioactive waste, the generic one, it is here. So the waste which is contaminated with radionuclides at activity concentration greater than clearance levels. So everywhere there are some levels strictly defined in all the countries and national regulations. But IAEA is publishing recommendations, and these recommendations will be in the next slides. These levels that are used, and most of the countries are using them, although they are extremely conservative. So the levels are so low that in reality, if the country has understanding and expertise, it can regularly, let's say, or readily use higher levels. Although, again, the population is not so well educated to understand what is the real hazard from the materials. And most of the countries, they use international regulations as they are published. And then everyone is silent, it's international regulated, it's very, very conservative. And the bad point is here, it's not that it's very conservative and, is extremely safe and more safe than needed, but is that there is clear acceptance and understanding. This is also a good thing, but bad thing it is that if you put too low levels, we have much larger volumes, so we pay more. And now imagine a civilization, a country, that has limited resources. And instead of using these resources, for medical care, for things that are really, really needed, we pump the resources in the radioactive waste. So this is the bad thing. But again, a good thing, the volume of the radioactive waste, it is so small compared with the volumes of other waste that this little bit bad thing. It is not so, you know, harmful for activities. So this is the definition. Pay attention to it because, as Professor Petrov emphasized, in reality, everything, including our bodies, are a little radioactive because the radiation is natural. We live with radiation, which is coming from the sun, from the stars, from the cosmic space. So when you are flying, the radiation is much higher than now when you are in the room. And this is natural. This is natural. In addition to this, you heard many times from papers that it's carbon-14 dating. So there is a constant content of carbon-14 in living species. And if a plant, a tree, anything which is alive, until it is alive, the content of carbon-14 is constant there. And after the death, there is no more exchange of matter in between the environment and the body. And we can exactly find when this piece of material from archaeology stopped to be alive. So it's dead. So then we look to the content of carbon-14, we know how it decays, and we calculate when it was alive. So we can identify some things related to religion, let's say. So it's a myth, Jesus Christ, or it's a reality, and some of artifacts, they are in line with these books and so on. So that's the definition. And now an important slide. So it's a little bit simplified. It is what is our approach when we deal with radioactive materials or with radiations. So it's written here, there is a more complex picture, I will show it tomorrow. This is simplified. So here we have, let's say, radiation source, something with radiation, from where the radiation is coming. Maybe it's a material, maybe it's liquid, solid, maybe it's an accelerator, maybe it's a nuclear reactor, maybe it's anything that produces radiation, maybe the radiation that comes from the cosmic space, or from the body of the person that is sitting near you, and so on. So we have radiation sources. Some of them are excluded from consideration, let's say forever and from the beginning. What kind of sources are excluded? Cosmic radiation. From the regulatory point of view, this is, we say, the God, but this is the nature. The cosmic radiation is as is. From time to time, we have a much higher level of radiation due to the activity on the sun, which is a star, and is providing the light and heat and so on because of nuclear reactions there, right? All the stars do that. No any consideration for regulation of these things. Or another example of excluded things, it is the content, let's say, of potassium-40 in our body, in the body of the humans. So a part of potassium, potassium-40, with the number 40. The mass number is 40. It's radioactive. It decays, and 120 approximately part per million of all potassium on the Earth, including that which is in our body, in our bones, everywhere, is circulating through the cells, is radioactive. And during the decay, it emits a very strong gamma photon, as far as I remember, 5 mega electron volts. You imagine it goes through everything. It's very energetic photon, potassium-40. It is not regulated. It's a part of nature. It is as is. We are living with it. And again, perhaps you, most of you are quite educated and heard about. Earth was formed 4.5 billion years ago, long time ago, and the half-life of potassium-40 is 1.5 billion years. So a part of it is already gone. But if you look to the other radionuclides, uranium-235, then sometimes about 1.5 billion years ago, it was so much uranium-235 that we know places on the Earth where nuclear reactors operated during 100,000 of years, even million of years, naturally in Gabon. You heard perhaps about that. So during rainy seasons, when the water was going into the rock, the water is a good mediator, like we use it in nuclear reactors. And the reactor started to operate. And they continuously operated, hundreds of thousands of years. And then they stopped. It was dry season, no moderation, and so on. So that's just to tell again that we have some radionuclides which are called primordial. They existed from the beginning of the existence of our Earth, and they still exist, and they are there. And some of them are excluded from this point of view, no reason to consider them. But other are considered. So when we look to the considered radionuclides, you see here they are separated in two. These are exempt from regulatory control, and these are going under regulatory control. Which of them are exempt? So we know for sure that everywhere in the waste we have some radionuclides, but regularly. So practically always, with rare exceptions, the content of radionuclides is high. So if the content of radionuclides is regular, it is very, very low, then they are exempt from the very beginning from regulatory control. We are living with them as they are. And the levels will be shown a little bit later. And if their content is higher, then they are under regulatory control with the regulatory organizations in Russian Federation. So there are offices of nuclear regulations everywhere. In Russian Federation, this is something like Gosatomnadzor, something like that, the name. So ask for participants from lecture, or some of you know because you are experienced people. But again, look, we are dealing with radioactive materials and they are decaying. So this time, the level is just going down, nothing we do. It's just decay. So this time, we are getting below the regulatory levels, these regulatory control levels, so we can clear them. So clearance and exemption are the same, but exemption is from the very beginning, no reason to take under the control the radioactive materials. Clearance, the material is under regulatory control. I don't think that you are working for nuclear power plants. At nuclear power plants, everything which is there created as the waste at the beginning has the label radioactive waste, and then there is a clearance procedure. So all the materials are checked to be sure that they are really not above the clearance levels, and there is an official procedure of the clearance of the waste. So in the operation reports of nuclear power plants, there is an entire column or division or a section of cleared waste, the waste which is, we say, non-radioactive waste or a cleared waste, because their radioactivity is as everything trash around us, natural, no any harm of it. I'm paying this much attention to this because in the nuclear waste management, this procedure of clearance, exemption first and then clearance, are really very, very important at the stage, exemption at the beginning, but clearance at the stage of decommissioning projects, when we have huge amounts of materials, and practically, let's say 80–90% of this material, it is cleared because, the building materials, they are there, they are declared as radioactive waste, but the clearance procedure show that these are normal materials. So this is a kind of scheme. This one in the column and in the right part, yes, if you look to the screen so you have a practice, some materials. And the exemption, it is here. We are checking with the levels, and then it's bouncing here. This is exemption, and these are the texts. And if not, they are under regulatory control. And this time, due to the decay, or maybe change of the levels, because the regulatory authority from time to time introduce new regulations. And then we have to be consistent with the new regulations. And then we can do the procedure of the clearance, which is that one. And these are the definitions of the exemption. The meaning is explained to you, right? And so things that are not really harmful are exempt. Things that were initially considered as harmful, but due to the decay became non-harmful, are cleared. So these are the meanings. The texts are here. And they refer to a so-called schedule, which is taken in the basic safety standard. The cover was shown above. So we need now to look a little bit to these schedules. What kind of these levels are these levels? So this is the definition of you see here, a practice or source within a practice may be exempted without further consideration for some or all the requirements of the standards under the terms under all reasonably foreseen circumstances. So there were considered all kind of scenario that the radionuclides from the exempt waste will somehow all possibilities, drinking, breathing, being in contact, sleeping on a pillow which has these materials and all kind of these things. And as a level of dose to us, to humans, was taken the dose of the order of 10 microsievert or less in a year. Micro means 10 to minus 6 power, right? 10 multiplied to 10 to minus 6 powers, that means 10 microsievert or less in a year. You remember the sievert. I hope you know these units. I'm not paying attention. So this is joule per kilogram. So it's for the dose that is absorbed radiation, the energy which is deposited in the cells in the body in a 1 kilogram of matter. Just a reminder. So that's the level that was for the dose. So the dose is that one. It's extremely low, so the next slide will show you that. But there are some scenarios which are called low probability scenario. So let me explain you one of that. So perhaps some of you, one of you, or maybe none, but maybe one or two of you are smoking, right? So when you smoke, you produce a little bit. When you smoke the cigarette, you produce a little bit, or better example, perfume. So mostly female. So you use a droplet of perfume, which is nicely smelling. And if someone with the perfume is entering into the room, almost immediately, you start to feel, this nice smell, which gives evidence that the molecules of the perfume from this very small droplet that in the morning, looking into the mirror, someone used it, this very small amount, now is spread in the entire room. Now the probability that this smelled from the entire room will be collected together again in the droplet mathematically is going to zero. No way. If it is dispersed in the air, these molecules, they will never. So mathematically is not absolute zero, of course. It's 10 to minus extremely large number, so practically zero. That never will occur. So that such kind of scenario are called low probability scenario. And within this low probability scenario, instead of taking 10 microsievert, it is taken another number, much more reasonable. All these numbers are internationally agreed, which is 1 millisievert in a year. Millisievert. This is more commensurable with the doses that we are, all of us, receiving from the nature. And there is also a note about naturally occurring radioactive materials. So let's discuss that tomorrow, after tomorrow. It will be a table a little bit below. So the tables. Dear participants, you cannot read from the room these tables, but you see some numbers. So what numbers are these? This is the table 1 in the schedule 1. So this is the first table that shows activity concentration and is given in becquerel per gram. You remember becquerel is 1 decay per second, right? 1 disintegration in 1 second. And this is activity, the total activity of the material. And then radionuclides. So it starts with tritium, the first one, radioactive element. And then many. So I put just 2 examples, so two parts of these tables. They have 2 columns. The first one is activity concentration. And the table 1.1, it is for moderate amount. So if you have a moderate amount of material, and if let's say tritium, if the tritium concentration is less than 1 megabecquerel per gram, then whatever will happen with this tritium, never anyone on this planet will receive more than 10 microsievert during 1 year. Because of that is exempt. So if you are working with tritium at this concentration, you don't need to go to regulatory authority and to ask permission. You do that because you are sure that no one will be somehow damaged by radiation coming from this very small amount of radioactivity. And you have here all kinds of some of them, you see that the activities are much lower. Tritium, it's example where the activity can be much higher. Or if you have the total activity, which is 1 gigabecquerel, then again is the same situation. So these are called moderate amounts. But in our practice, there are situations when the amounts are not moderate at all. So let's say if you look to this coal, which is produced at coal-fueled power plants, which produce electricity burning the coal, then you have mountains, millions of tons of this ash. So they are not moderate at all. For this case, there are other tables. So this is 1, 2, you see, where you have just activity concentration. So the total amount doesn't matter because there are mountings, but the concentration must not exceed, and you see instead of mega, it is just 100 becquerel per gram for tritium. And all the numbers are here much lower. So it was calculated by the teams of international experts working for IAEA, an International Commission on Radiological Protection, using all kinds of tools, scenario considering, and etc. So these numbers are well justified and recommended by the ICRP, International Commission on Radiological Protection, IAEA, to everyone to be used as exemption levels. And countries do that. So if you take a regulatory document from a country and you check these numbers, they are very close to those, or 1-to-1 taken. Again, there are many reasons to just take, although they are very conservative. And the comments about how they were calculated. So I put, for curiosity of you not entering now into the details, the references about the derivation of activity. So these are publications by IAEA. So that one is published in 2005. So how these numbers were calculated, what are the basis of having this number just described? In simple words, the total dose during 1 year will never exceed 10 microsievert. And for low probability scenario, like, this dispersion when no possibility to collect back the radioactivity, is 1 millisievert per year. And for naturally of natural origin, naturally occurring radioactive materials, like I noted to you, potassium-40 is a naturally occurring radioactive materials. So you see here 10 becquerel per gram. That's the end for in the decay series of uranium and thorium. You have 1 becquerel per gram. So these are the recommended exemption levels. This time, from radioactive materials under the control, they can, due to the decay, come to these exemption levels, and then you must pass the clearance procedure to get approval from regulatory authority, and then you can formally, officially, legally get rid of the radioactive waste, changing the label and saying this radioactive waste is not anymore radioactive waste, is cleared waste, because the radioactivity now is night. It is even more clean than many of naturally occurring materials. On next week, I will show some examples, not to scare you, but to make you aware of the real situation. Again, the information on that, and here there are the comments taken from international regulations. The point that I wanted to give you the additional information, these slides, are the 2 references here. about the derivation of these levels for moderate amount and for bulk amount, and the situation when you are dealing with the combination, not one radionuclide. The table is for one. If you have several, you need to calculate this sum. You take these numbers from the table. This is the fraction content of each of radionuclides, and then you calculate the sum, and it will give you a reason for exemption and clearance when you calculate all the doses from all the radionuclides. And this slide is also given to you to give you actually the flavor, what is the meaning of moderate amount. So what is the moderate amount? Because for a person, let's say for me, moderate amount, it's maybe something that I can, by the weight, it's still under, so maybe some 40 kilograms. So if a heavyweight champion can take 100 kilograms, I can maybe some 40, 50 kilograms, not more. But in reality, the IAEA consider as moderate amount something of the order of 1 ton, 1,000 kilograms. If you go above this is bulk. This is not moderate. I'm sorry. Then you must go to the table 1.1 and use much more restricted levels from the table 1.2. Consider that is a bulk, a lot of material instead of moderate, which is by IAEA something below 1 ton approximately. So that's the message that I would like to pass to you in this respect. So for naturally occurring radioactive materials, are likely for low probability scenario, all the international regulations allow to use, instead of extremely conservative amount 10 microsievert, 1 millisievert, so 100 times higher level. Although he also specifies that should be considered case by case. Case by case. If you have expertise in the country, please apply to different materials specific. So the volume of these materials is huge. In many cases, if you will apply the regulations from nuclear industry, we must stop the activity of industries. We must stop operation of coal-fueled plants. They cannot comply with our nuclear regulations. They will be stopped immediately. Or production of fertilizer or oil and gas industry, they cannot work under the regulations from nuclear industry. Nuclear industry operates under much more strict regulations. It's as a specialist. So the courses on radiochemistry, you understand you have a fence of a nuclear power plant, let's say, and you take the same materials in the fence, and then this is radioactive waste. If it is the same material but out of the fence, so you apply other regulations, not nuclear, it's not radioactive, and nobody cares. So the society supports this approach. Everybody is scared of nuclear power plants and so on, and nobody is scared of chemical industries and etc. Okay, so these are the comments and the slide that will a little bit demonstrate to you the unreasonable conservatism in defining these clearance levels. So this is the slide taken from Japan. They published this to show to the general public what is radiation, what we are dealing with, etc., etc. And because of that, the reference here is to a Japanese side. So this is the range of natural radiation, the doses that we are receiving as we live in the nature. So globally for anyone on the Earth, we are receiving 2.4 millisievert each year of radiation. We are absorbing this energy, this is deposited in us, and this is natural. And for your information, there are many experts in biology which consider that radiation of this level is not harmful, but it is maybe a necessary part of the life. Maybe that the life could not even develop without this radiation. There are such claims, publications, etc. I'm not an expert in this area. I can tell you that I put in my book that I show you the cover there, just a page about that. I put a published statistic of the people after a bombardment of Hiroshima and Nagasaki in 1945. There is statistical material of a life time of persons that were irradiated due to explosion of these bombs. And the people who received the doses even a little bit higher than here shown, due to the bombardment, their life is much extended than average life of Japanese on the island. And this is just one example, but there are many others that show that radiation of this level. So let's say this level, it's a place in Iran where the radiation, it is even here, that one. So it's 100 millisievert per year. But statistically, there is no more cancer there in this area in Iran than in other places. So we cannot claim that this is really helpful. But anyway, the normal, let's say, range, it is from here to here. So up to 10 millisievert per year. This is global, 2.4 millisievert per year. This one, 6.9, which is full body CT scan. So computer tomography scan, medical procedure. Something like that, it is for the place where I'm living in Sheffield. We have here the old mountains, a lot of granitic rocks, and they contain, this uranium, and because of that, radiation is something like here. In United Kingdom, in Sheffield, this area, so that's Pennine area, so-called. So this is the range that everyone is living with, this range, natural, right? And if you look to this arrow now, look, this is this targeted annual level of safe radiation dose, which is recommended and used to obtain clearance levels. It is 1,000 times less, 1,000 times less than natural. It is too conservative, dear colleagues. It's not because I invite you, the regulations are regulations. We must follow regulations. But be aware as experts that they are very, very conservative. And also you understand that if it is too conservative, then you put too much resources in complying with too conservative numbers. So that's the information about these levels. So now, after this introduction, let's move to the international regulations. So there are many. Because of that, the lecture is split into two. And maybe the other lecturers also will give you parts which belong not to technology, but to regulation. So the international regulations, they are actually coming from International Atomic Energy Agency, which uses other recommendations from International Commission of Radiological Protection. So it's using national expertises, of course, from the world. It's not inventing something. Everything which is created in the IAEA, it is coming from the so-called member states, from expertise of nuclear powers. So that's Russian Federation, where you are now sitting in Moscow, United States of America, France, United Kingdom, of course, and Japan, and all the countries, practically all the countries have equal rights, if they have expertise, to recommend, to assist agency, and even to insist on something to be in international regulations concerning levels, etc., etc. So these are formed by international consensus. It's not just, coming from Vienna and follow them. No, there is a consensus. There is a long discussion in between the experts who created the drafts, and then the drafts are going to the countries, discussed, and etc. And only after that, we got these Bibles, let's say. So not Bibles, but regulations. And because there are so many, they are organized in a form of a pyramid. So it's actually turn pyramid, but it's better to look here. So on the top of the pyramid, we have the basic document, which is called safety fundamentals. And then under it, we have general safety requirements, things that you must do. And some of them are general, some of them are specific. In red color, you see. And you imagine there are not just 1, 2. There are few, several, let's say. And then in green color under them, there are general safety guides. So it is better to follow these guides. So these are not requirements, they are guides. So there is a lot of practice. The people know how to do that, and these are the guides. So it's better to, to follow someone. It's better to ask someone how to go from here to here. Then you do that safely, because many already passed this way. And the slide actually is, if you are lucky and are exempt, end of the job. After the decay again, clearance, end of the job. There is no more radioactive waste, so you are cleared. But if not, the practice is under regulatory control. And how to ensure safety? The recommendation is use IAEA safety standards, use international regulations, and the countries do that. So it's not just this basic safety standard. All IAEA standards are very often adapted to the needs of the country with necessary amendments, because situation is not everywhere the same, and then used. So this recommendation, it's a viable one, which is that one that works. So it was this picture now about the requirements. So there are general safety requirements, and there are 7 of them. A little bit more information about them will be given tomorrow in the morning. So you see here, they are called parts. So there are 7 parts, 7 parts. So 1, 2, 3, it is radiation protection and safety of radiation sources. This is that one that in the past was termed basic safety standard. But so that's legal, regulatory requirements, leadership. Then you go to this radiation protection, and then predisposal management. You'll have a lecture about that. Decommissioning activities. A lot of resources are now in the decommissioning area. Very big projects, big opportunities for career of the experts that have good education. So large projects. It's similar by the magnitude of the resources to the construction of nuclear power plants. So these are really big projects that require hundreds, if not thousands, of experts to be involved in these projects. And emergency preparedness and response. So general safety requirements. And one of them is the basic safety standard, that one. And then there are specific, so not generic, specific, like site evaluation. It's just for the site. Or safety of nuclear power plants, which is divided into design and then commissioning and operation. Then safety of research reactors, because research reactors are very different. The core, active core, so it's not to produce energy, not same power, not just to produce energy. It is to do research, maybe to generate some medical isotopes like that, so different. Because of that, there are specific requirements for that. Then safety of radioactive disposal facilities and safe transport of radioactive materials. I will tomorrow speak more about. This one is specific, but has the level of international law. So it's very, really important, because we have transborder movement of radioactive materials. And then you see here something, collection of safety guides, and actually technical documents of agency are also kind of guides, where you have much more details on technologies, etc., etc. Okay, so in international regulations, we are starting with the very top of the pyramid. So everything goes under there, which is called this document Fundamental Safety Principles, and is not for radioactive waste. It is actually fundamental safety principles for use of nuclear energy. So the document is a very short one. It describes this fundamental safety objective, which is to protect people and environment from harmful effect of ionizing radiation. And it describes the 10 basic or fundamental safety principles, which are extremely important. It is like, perhaps all of you are so in a Russian Federation, you drive the right side of the road. This is a principle. All kinds of regulations for for motion on the roads are using this principle. So the vehicle are moving on the right side of the road. In the United Kingdom is another principle. We are driving on the left side of the road. And this is a principle. And we should not confuse them. So principles are very important because everything is based on principles. And there are 10 principles that if we follow these principles, then the regulations, everything are based on these principles, and we stay safe using correct principles. And you see here 10 of them. So the titles are responsibility for safety, role of government, leadership, and management for safety, 3 at the beginning. Then we have other block, justification of facilities and activities, optimization of protection, limitation of risk to individual. And then protection of present and future generations, something unique for nuclear things, because of specific action of radiation documents that can extend not only through the borders but even in time due to the mutations. So some of chemicals cause mutation, so change in genetic code, and radiation do that. And the last block is prevention of accidents, emergency preparedness and response, and protective actions to reduce existing or unregulated radiation risks that exist as they are. So explanation before we go to going through each of these 10 principles briefly, of course, no to each. So they are applied for all kinds of facilities that is anything radioactive there. So here is the long text explaining that irradiator, nuclear facilities, mining, and raw material processing. So all kind of these things where we are dealing with something with radiation. And activities. So production, use, import, and export. So if you will work as an inspector for a border control in a country, and because radioactive materials are crossing the border, then these regulations which come from IAEA apply. So they are really not just within the nuclear industry. So facilities and activities, including those that at the glance view maybe it's nothing there radioactive, but can be. And this is the explanation where what kind of facilities and all kind of activities. And in a Russian language, some of you are better of this language. Also, I can speak. It's a language that I know very well, Russian language. And in a Russian language, both for safety and security, we use the same word. We say безопасность. That means both safety and security. In English, we have 2 words, so safety and security, and the standards, the principles, they are valid both for safety and security, and in order to ensure security, provisions are also taken, controls of access to prevent even access to this material, so loss, removal, etc., and arrangement for mitigating the consequence of accidents and failure. So that's in order to ensure the security of the facility where we have something with radiation. So the fundamental safety objective is to protect people and environment from harmful effects of ionizing radiation. So the radiation is so strong by energy of photons that is capable to ionize atoms. So we are speaking about really very strong radiation from the point of view of photon energy. And when we speak about the harmful effect of ionizing radiation and limitations, we should not forget that this has to be achieved without unduly limiting the operation of facilities and conduct of activities. Because the simplest thing, it is to prohibit. And in many cases, there are such incentives of regulators. If it is not any radioactivity, that I can sleep, without any care, because what to control? There is no any radioactivity. So but there are some activities that they cannot they cannot be carried out without use of nuclear energy. And practically all of us, we know about nuclear medicine, which is saving the lives of the people. So of millions of the people that they have a normal life because of nuclear medicine. And first of all, the diagnosis, identifying the organ that is malfunctioning. And this is practically everywhere. And without it, you know, the life now is very long and on average. And it's due to the including, of course, development of all medical care, but the nuclear part, it's something you cannot take it out from there. And there are very active materials there in nuclear medicine, sealed radioactive sources, gamma knives killing the cancer cells, and many, many other things that need nuclear energy. And if in the morning, Professor Petrov explained to you the nuclear power. So again, let's prohibit everywhere, like the Germans now, they want to go green. But do they think about the future of the future generation in their country? How they will be able, you know, because they are contaminating the environment with the radioactive materials from burning of the coal. They do that. Maybe you don't know, but France, European country, which is using most of the energy in France is produced by nuclear power plants. It's the question about 70, 80%. You know that, you heard about that, right? I think so. But perhaps you don't know that in Europe, France is the greenest country, the most clean country. And the large reason of that, it is that because they use nuclear power plants. They are selling electricity to there and there. And please, why not? So I'm convinced, of course, but not just me. Most of the experts that deal with the development of civilization, they know for sure that without the nuclear power, there is no possibility to develop the civilization on the globe. And colleagues, I'm sorry, I have some projects, I'm communicating with the experts. Look to the Middle East. Look to the country like I don't know, some Arab countries, they have a lot of gas, a lot of oil, but they develop nuclear power. They don't need it today, but they think of development of generation tomorrow, after tomorrow, of even your grandkids, grandchildren. They think, because these are things that is for the future, and you have the basis of that. So that one in red, we should not use the way of, you know, stopping, because by this we are doing very bad things for the civilization. Of course, we must do things safely and follow all these things. Okay, so I'm going too much through the time which is given to me. So here, to achieve that standard of safety and to do this reasonable, first, radiation exposure, it is controlled to the people and the release of radioactive materials. Then the likelihood of events like happened in Chernobyl or in Fukushima is restricted. So a proper control will stop these things. Perhaps you heard that both Chernobyl and Fukushima occurred because of the breach of regulations. Because of the breach of regulations, this happened, unfortunately. So these catastrophes are man-made. Of course, in Fukushima, that was the earthquake, the tsunami, and so on. But the extension of operation under the conditions of tsunami and earthquakes was not justified in Japan. So again, it was a breach of this thing. And if the consequences will occur, then to mitigate these consequences. So I'll be a little bit shorter, just not to bother you too much, because it's a lot to speak about and so on. So we have 10 principles. So the first one, it's about responsibility for safety. So the prime responsibility for safety in the principle says must rest with the person or organization responsible for facility and activity. If you work in a laboratory with radioactive materials, you have regulators, all kinds of inspectors, etc. They only inspect, control you. Responsibility is with you. The person who works with radioactivity is that one which is responsible. So if something will happen, you know, without the following the regulations, then the person who breached the regulation will go to the jail. So you see here, authorization to operate a facility or conduct activity may be granted to an operator, licensee, but the licensee cannot delegate his responsibility to someone. He can ask someone to come to work in his laboratory, and responsibility will not be delegated to him. You see here, cannot be delegated, stays with licensee. The person who received the license, it is responsible for the safety. And then there are explanation, what are the responsibility? We say that this is operator, the person who works with radiation, with radioactivity is operator. And you see here, competence, establishing and maintaining, adequate training, procedures and arrangements to maintain safety, verifying the design, adequate quality of facilities, ensuring safe control of radioactive materials, and ensuring safe control of radioactive waste. We came to the point of dealing with radioactive waste that is generated. If we work with radioactivity, we will have byproduct, radioactive waste, and it is under responsibility of so-called operator. Then we go to the principle number 2 about the governments. And it says that effective legal and governmental framework for safety, including independent regulatory body, must be established and sustained. And you see, independent. In Chernobyl, the regulatory organization who signed the permission to do experiments that ended with the catastrophe was not independent. And he signed the documents without having, possibility to reject it and to stop these experiments, unfortunately. And it was revealed that in Japan, it was not full independence of regulatory organization from operators of nuclear power plants in Japan. And formally also, it's a kind of the breach of this independence. That is recommended. And then the government and regulatory bodies have the responsibility in establishing standards and regulations, things that I am explaining in my lectures to you. So that is the Hammurabi column, the first laws known by civilization. A copy of this quite tall, the basalt column, which is available in the headquarters in Vienna. It's a copy. The original, it's not here. It's in Iran. Where is it? But the copy is in headquarters of Vienna, and the laws. It's like coming from the god, through the king Hammurabi of Persia. So initially it was discovered there in Persia, in old Persia. So the first law, so because that it's this symbolizing the laws, role of government. And then here it's about the regulatory, what are their responsibilities, what they do. So they also consult parties and public about what's happening in a nuclear facility, object, etc. Principle number 3, it's about leadership and management for safety, and says that leadership and management must be, for safety, must be established and sustained in organization concerned with and facilities and activities that give rise to radiation risks. The question under principle 3, it is about management systems. This is a very important part, administrative part. But if you have a proper management system, then you will not breach, this previous principle. So you will have a real independent system, etc., etc. And it's also the question about having a good so-called safety culture. And safety culture is not, coming immediately from my lecture or from the lecture of other lecturers and so on. This is something that goes through even generations. It's like, in nuclear industry, it's a very young one. It's not a question of very long, but we have the culture of producing wine, let's say. And where are the best wines produced? Where is the safety culture and production of the wines, right? So they are coming, from France, from other countries. They have from Caucasus region, let's say Armenia, and other places. The place where I was born in Moldova. And there is a real history. Georgia is known to everyone as the best wines. So there's a very, very thousands and thousands of years education, and the safety culture is through generations. And then this culture allowed to operate everything in a good way. And of course, the safety assessment, it goes under this principle. And then we have in the safety assessment, there is a schematic of things are done in the safety assessment. So normal procedure, then failures, and so on. These are under this principle. We go to the 10 of them. So, I'll fit into my slot, so sorry. So principle number 4, it's about justification of facilities and activities. So if things are not really needed, don't do them. But if, like nuclear medicine, we must use it because that's for benefit of patients and society. So let's say society benefits from the nuclear energy. Maybe that today, some of participants are from Belarus. I think that is a good example of thinking of the benefit of society. So maybe today it's a big investment in nuclear power, which needs, much resources. But society, not tomorrow, but through years will return back all the investments in the nuclear power because this is a clean, cheap, useful source, effective source of power for the country and for the society. And then we have the persons, and in the persons, sometimes we are delivering to the persons extremely harmful doses. We are killing by gamma knives the cancer. The doses there focused on a small piece of the body are deadly. There is a necrosis of the cancer, but this is for benefit of the person. Optimization of protection. So we should, so I put, this schematic, it's a balance. If you can do the job by one person, why to submit 10 persons and to irradiate all of them? No need to do that, right? And so on. These things, optimization of the protection, go under the principle number 5. Principle number 6, with this funny cartoon, it's about limitations of risks to individuals, to every person. They are coming, given in this table, from the International Commission on Radiological Protection, and then are reproduced by IAEA, by national regulations. And you see here, occupational doses permitted are for personnel which take some risk. They are paid for that. So I worked 20 years in nuclear industry, and I was paid for this risk. And the regulations are such that 20 millisievert per year, so average is 2.4, right, on the globe. But for personnel, can be 1 year, during 5 years, even 50, so much higher. Then will be some additional risk because of, but for public, you see here, the doses are, let's say, even ridiculous small. So they are followed as given in this table. So may slightly vary from national values, but very close to these that are given here. So the whole body very limited. But if you go to some parts of our body, let's say skin, it is renewed in a couple of months, we have a new skin. So then we can afford having a much higher dose, let's say on a hand somewhere, because we will easily have no any harm from radiation because of that. These numbers are higher. Again, this time its repetition is to show where is it. It is here for public. You see. So this is the maximum annual exposure for general public, excluding medical procedures. And medical procedures, I informed you that for gamma knife you have huge doses. Principle number 7 is about protection of present and future generations. And you see, people and the environment, present and future, must be protected against radiation risks. I can give you an example because I participated in a big project in a good time of good relations in between the Russian Federation and the United States of America. So at that time, it was even a joint project in so-called Gore-Chernobyl project. And I'm quite aware of these things which happen in Hanford, in the United States of America. So the point was that there in States, they calculated the doses after disposal of the waste there in the tanks in near surface repository. And they found that today is everything good during hundreds of years, but after 1,000 years, the probably not the real one, dose expected via scenario to the population will reach the current level, which is defined for the people in the United States of America by the EPA, Environment Protection Agency. And they said, cementation, no, stop. And nowadays, now is under the testing to start operation, the largest in the world vitrification plant. Just in order to provide in the future, not now, the same dose like today. Because the principle is that we cannot breach our principles, these regulations, and they follow IAEA recommendation in the States. This is the example. Principle number 8, it's about prevention of accidents. So all the efforts must be made, and the primary means of preventing and mitigating the consequences is defense and depth. And the symbol is matryoshka, defense and depth, many barriers. One of the barriers is design and engineering features. And also the first you see, it starts with effective management system. A good management system is one of the barriers. Principle number 9, it's emergency preparedness and response. From time to time, things happen. Causes are different. We have many examples of things, and we must be prepared locally, regionally, nationally, and internationally. And in Vienna, in the headquarters of agency, there is an entire division which deals with emergency preparedness and response everywhere. There are inspectors, there are experts which advise countries how to be properly prepared for emergency situations, not to be in a big surprise and to know what to do. The last one, it is about existing unregulated risks. So for radiation of natural origin, where we have, let's say, emanation of radon, human activities conducted in the past before 1963, even nuclear bombs were tested in the atmosphere, and a lot of not a lot, but all the currently cesium-137, strontium-90 that we observe in the environment, in soil, in the water, it's from these tests. But now we live with it. And remediation measures following an uncontrolled release, like aftermath of things like in Chernobyl and Fukushima that happened, these things. So, conclusions. 10 safety principles of IAEA safety standard, safety fundamental 1, the first one, are the basis for requirements and guides of peaceful use of nuclear energy. And the standards recommended by IAEA reflect consensus on what constitutes a high level of safety. And this is a global consensus. So we have 178 like that member states. So these are members of IAEA. Almost all the countries in the world, not all of them, but most of them are already members of IAEA, and this is a global consensus of these standards. This is the link but nowadays I put it because from my past activities it was very useful to click and to get to all the standards. Nowadays you can find everything via Google, and that immediately you will get everything that you need. So dear participants, many thanks for your patience. I am stopping to share this business, and if you want something, but it's not finished. Tomorrow in the morning, I will continue with you to
Thank you very
this
much.
stuff for you.
Does anybody have questions? I have one small question. Maybe it's not so small, but when we are talking about the newcomers countries, what are the main difficulties, maybe, or problems to implement directly the safety requirements of the IAEA? Just to take them and apply.
Yeah. So many thanks, Vladimir and dear colleague. Vladimir, it's a verb, but it's useful for the auditorium, definitely. So the newcomers, of course, are in a difficult position because they have no experience, so they are really newcomers. They, let's say, are starting from scratch. But the good thing it is there's a lot of experience in Vienna in IAEA. And there are dedicated commissions, there are dedicated publications of steps that newcomers should follow in order to get on board, to start becoming of nuclear energy user. But this is actually for the countries that want, let's say, to start operating a nuclear research reactor, a power reactor, so to be a large user of nuclear energy, not like just nuclear energy. For the just nuclear energy, of course, again, in Vienna, there are dedicated sections that deal with the nuclear medicine and including radioactive waste from the nuclear medicine. So this is a site which is a subsite of agency that is like health, something like that. And IAEA it's conducting workshops, meetings, where when the countries, why is good to be a members of IAEA? Then you have the possibility to join these meetings, these workshops. So then the medical personnel are participating in various. So it's not just to deal with the radioactive waste, it's also for irradiation of tumors, for utilization of accelerator for something, for diagnosis. So it's much, much larger. My lecture is focused on nuclear waste, of course. But again, these things are, it is recognized nowadays is better done through the IAEA and very often can be done even on the expenses of IAEA. So IAEA it's conducting and is organizing national projects. And I was born in Moldova, so it's a small country with very small resources, but it has a national project with agency, and the agency is providing resources and even provided a big accelerator for they have several centers for the treatment of cancer patients. So that is mainly for the question of small countries to get assistance and to proper. So expertise and even funds to develop something are obtained via IAEA. But just to finish, because it's a big topic, just to finish, IAEA, you are when IAEA conducts workshops, and it's encouraging organization of bilateral contacts. So now you came to Russia. It's a very well-developed country, and if you see possibilities, and some of you maybe are big administrator, I don't know, use these possibilities. Bilateral, it's something which is very much encouraged by the agency. So agency is not providing full funds, but it's encouraging to establish some initial contacts, and then you go just by contacting and so on and so on. And because I'm aware, Russia, for example, provides very big assistance in developing nuclear power plant. Some initial investments are covered by the agency because it can be then a mutual beneficial business. So, but this is a smart approach for all big business projects. So thank you.
Okay, thank you. Any more questions? Yeah.
It was something in the chat. I'm not sure that is a question to me. I don't see it. I don't know where is it in my. If it is something, Vladimir, just look if it's important. If not, then.
Just a question about a calculation in the table 1.1 about the moderate and the bulk materials. If we make if we divide the concentration, the activity to the concentration, let's say for the tritium is 10 to 9 divided by 10 to 6. Is this value
you get,
some
you
practical...
get 1 kilogram. You get 1 kilogram. So
yes.
What is the question?
This 1 kilogram has some practical meaning. Is the lower level of the moderate material?
No, it does not. No. It's not. So the agency in the regulation specify either war. So if you are with the first column, okay, you can work. If you work with the second column, you can work. But if you go to the amount which is 1 ton, not 1 kilogram, then not. And these are recommendations from the agency. But in the national, I don't know from which country you are. It can be that in your country is there 100 kilograms only. I don't know. You need to check and to be sure that you are not breaching your national regulations, because agency, again, these standards have only the standard on transportation is international law. All other, they have the recommendation character. and you have to comply with your national regulations and everything that you do in your country.
Okay, I'm from Greece, and we have also this what you refer to 1 ton of a material is the limit between bulk and moderate.
Yeah.
And another thing
It
is,
comes from agency. It
Yeah.
comes from agency.
another thing is, can you comment on the solid word on this table? It refers only in solid and not in liquid material.
Right.
But
That's
what is
right.
going on with the liquid?
Yeah, that's right. With the liquid, at the beginning of this year, IAEA has published 2 documents. Tomorrow I will give you the exact references. These are called safety guides, where they explained what to do with the liquids. In principle, the approach is similar to that, but you imagine when you calculate things of the doses coming from the liquid and from the solid, they are different. Because of that, particularly in national regulations, the numbers are not the same. And since the guide it's national rather than international, then it's important to follow national regulations. So it's really the table are for solid that you just saw. So in many cases, if you have the same liquid and you want to be under regulation, you need to solidify it and then you can get rid of it. So not to breach national regulations. So the solution is very easy. But if you want to know more details, then in the lecture tomorrow, I will give you these 2 safety guides that just appeared with the explanation.
Okay, thank you very much.
More questions? So there is a question in the chat. Just a moment. So it's about the safety standards for the nuclear energy to produce green hydrogen. So are there
And what the
any
question is about, what they want to know.
safety standards related to nuclear energy to generate green hydrogen?
They are exactly the same. So it's no difference. These are standards for safe use of nuclear energy. That's it. It is for any purpose, including production of hydrogen. The part which is radioactive is this.
Okay, thank you. If there is no more questions, let's thank Professor Rajavan one more time. Thank you.
Okay, then see you tomorrow.
See you tomorrow. So now we have a short break before the next lecture.
Rosatom is a leader in the global market of nuclear services and technologies. The corporation demonstrates by example how to reliably control and safely use limitless nuclear energy and goals developed.
Идет, когда надо ссылку транслировать поиску. Если ты еще раз поделиться,
Поделиться надо, да?
да.
Rosatom is a leader in the global market of nuclear services and technologies. The corporation demonstrates by example how to reliably
Раз, раз, раз.
Rosatom is a leader in the global market of nuclear services and technologies. The corporate
Раз, раз. Раз. Так, а сейчас и...
Rosatom is a leader in the global market of nuclear services and technologies. The corporation demonstrates by example how to reliably control and safely use limitless nuclear energy. The corporation's foreign portfolio includes 34 state
Раз, раз.
So, good afternoon, ladies and gentlemen. My name is Ella Barinova, and I represent the fuel company of the State Atomic Energy Corporation, Rosatom. Today I'm very pleased to accompany you on our virtual journey through the Rosatom's experience in the field of nuclear decommissioning, radioactive waste management, and contaminated sites remediation. During our journey, we will highlight the key aspects of our work and also talk about the areas of expertise of Rosatom in about its technologies and products. So let's start from the small introduction.
Rosatom is a leader in the global market of nuclear services and technologies. The corporation demonstrates by example how to reliably control and safely use limitless nuclear energy. The corporation's foreign portfolio includes 34 state-of-the-art power generation units in 11 countries. Rosatom provides its partners with a unique offering: turnkey nuclear power plant construction and service at all stages of nuclear power plant lifecycle. Managing the lifecycle of a nuclear facility, from the decision to build it to decommissioning, is an important strategic task that entails ensuring sustainable development of the nuclear power industry. Solving tasks regarding safe and efficient decommissioning and shutting down nuclear and radiation hazardous facilities, as well as issues of radioactive waste management and site remediation, are priorities and promising areas of activity. In 2019, fuel company TERL was appointed by State Corporation Rosatom to be the industry integrator in the following business area: nuclear decommissioning and associated radioactive waste management. The fuel company of Rosatom TERL is one of the world's largest suppliers of nuclear fuel. TERL is a monopoly supplier of nuclear fuel to all Russian nuclear power plants, ship and research reactors. TERL fuels MPPs in 14 countries. That equates to every 6th power reactor. TERL incorporates enterprises that specialize in making gas centrifuge machines, uranium enrichment, and fabrication of nuclear fuel, as well as research and development organizations. The Rosatom Decommissioning Integrator is a one-stop shop for cooperation between Rosatom and its partners and customers on nuclear decommissioning and radioactive waste management. Accumulates, centralizes, and consolidates the competencies of nuclear industry organizations in the area of nuclear decommissioning. Develops a comprehensive product offering a full cycle of services from pre-design studies, design documentation development, to dismantling of equipment and structures and site remediation after decommissioning is completed. Coordinates nuclear decommissioning activities, optimizes the allocation of industry resources, develops human resources potential, and creates educational platforms to improve employee competence and retraining. Builds supply chains in Russian and foreign markets, finances research and development projects, contributes to the achievement of the Sustainable Development Goals developed by the United Nations.
So now let's move to our technical tour. There are more than 50 companies in Rosatom that are involved in the business of nuclear decommissioning. And all their competences, which are very valuable, make more than 60 working products, which we successfully implemented in more than 100 successfully implemented projects in the field of decommissioning. As you can see, they were realized in many countries, more than 20. And they very different nuclear facilities were successfully decommissioned. Now let's have a look at what nuclear decommissioning is and what is its relevancies.
Nuclear power is an essential component of the global energy complex, accounting for about 17% of electricity production. It can be a guarantee of the economic and energy independence of states, provided the safety of its use is ensured naturally. This is the relevance of decommissioning. We should be able not only to build, but also to competently complete the life cycle of a facility. There are now about 138 nuclear power units in the world, not including experimental, industrial, research and transport reactors, as well as sites which have been shut down, are in various stages of decommissioning. One of the leading scientific centers in the world's nuclear power industry, the Radium Institute in St. Petersburg, celebrated its 100th anniversary this year. It wasn't the only organization in the Soviet Union that used radiation hazardous materials in its processes. Today, there are over 100 such enterprises in Russia alone. Uranium mining and enrichment, production of nuclear fuel and ionizing radiation sources, generation of electricity and heat at nuclear power plants, storage of spent fuel, disposal of various radioactive wastes. All types of facilities eventually end their operation and must be safely decommissioned and the area remediated. Just imagine a natural park could appear in the place where the nuclear power plant is today, a garden city or another Disneyland. You're probably asking how's that possible? The answer is here at 12 Fuel Company, where Rosatom is creating a new resource and scientific base.
So, the decommissioning process is a very important part of the life cycle of the nuclear facility. According to the existing international and national experience, it can be implemented in two very different ways. The first one is the in situ disposal, when, according to the technical and radiation safety and financial reasons, it is more preferable to make the site safety, but without excavation of the building constructions and equipment. We here will see you two successfully implemented projects which concerning in situ disposal.
In situ disposal of a nuclear facility. This approach is adopted for decommissioning of industrial uranium graphite reactors, and Rosatom already has such experience. Remember the Disneyland thing? We're already one step ahead. It's a small hill now, but once upon a time, the Siberian Chemical Combine's first two-purpose industrial reactor was located here. The pilot and demonstration center for decommissioning of uranium graphite nuclear reactors was the first to gain experience and completely decommission this type of reactor in 2015. During implementation of this unprecedented project, Rosatom specialists did a huge amount of research, the results of which justify the safety of the adopted concept and design solutions. The decommissioning service worked out and implemented the technology for the creation of external and internal safety barriers during disposal of the reactor unit and performed a full range of practical works. The E12 industrial uranium graphite reactor, commissioned in 1958, was shut down in 1990 and disposed of in situ in 2015. On the site of the nuclear reactor building E12, there is now a special radioactive waste preservation facility in which radioactively contaminated elements of its structure are reliably isolated from the environment. Before, when there was a reactor building at this place where we're standing, the permissible operating time was 7 hours. Now, after the completion of all the work, the background radiation has dropped 8 times. Here, the natural background radiation is the same as at the whole site. All non-reactor equipment in the reactor building was dismantled, containerized and placed at a storage site. The lower elevations were backfilled with barrier materials based on natural clays. A specially selected and treated composition using a special technology was filled into the reactor. It's not just filled in, It's compacted and an engineering barrier is created. It prevents radionuclides from escaping from the metal structures of the reactor shaft, from the graphite stack, and if it happens that radionuclides escape, it absorbs and doesn't release radionuclides into the environment. Considering experience of technology on battery materials at the site at Sevets, we started decommissioning another industrial uranium graphite reactor for the mining and chemical combine in 2013, when the mining and chemical combine received a gold medal in the energy category at the Inventions Geneva exhibition for its patent, method of decommissioning a uranium graphite channel type nuclear reactor. The uniqueness and at the same time the complexity of this work lies in the facility's location. It lies in an underground mine in a rock massive at a depth of over 200 meters. There is a clear connection with the name of the Rosatom State Corporation's division, Environmental Solutions, which includes the mining and chemical combine. Today, the mining and chemical combine's activity is centered on the environmental safety of nuclear technology. The main source of radiation hazard is the reactor graphite stack, that is, the reactor core. There, a nuclear reaction was going on for decades. The main task of decommissioning is to create a protective barrier around it, which will reliably prevent radionuclides migration for the entire period of hazard. In fact, it's necessary to build an absolutely hermetic and immovable architectural structure around it, which retains its protective properties and also takes into account possible geological changes. All the nuclear fuel that was in the reactor at the time of shutdown was unloaded and reprocessed at our radiochemical facility. Radiation-contaminated equipment involved in the main technological process was dismantled from the new reactor sections as much as possible, so that the sections could be subsequently filled with barrier material. To prevent natural degradation of the existing metal structures, the sub-reactor section was filled with high-strength reinforced concrete. One of the main tasks was to localize as much as possible those radionuclides that had accumulated in the graphite stack throughout the reactor's lifetime. To do this, we solved the not exactly trivial problem of supplying barrier material. The band-free filling of the graphite stack and sections involves creating a monolithic structure that prevents the radionuclides in the graphite stack from spreading into the environment. The option of radiation-safe in-situ disposal of reactors eliminates a significant amount of radiation hazardous work and avoids the creation of additional facilities for the disposal of highly radioactive waste from the graphite stack bricks. In addition, the presence of a natural outer containment in the form of a rock massive over 200 meters of granite above the facility is also an advantage to this decommissioning option. Taken together, all this will ensure compliance with modern requirements for radiation safety and prevent releasing radioactive substances into the environment.
So here you have seen two examples of successfully implemented project of in-situ disposal. Then it was technically, economically reasonable. But of course, nowadays, according to the international recommendations, the liquidation of the nuclear facility is a more preferable option. It can be realized in two ways. The deferred decommissioning option, when after the shutdown, the transmission period includes making the nuclear safe condition of the facility, and further decommissioning works are planned to be made in several years. Sometimes because of the absence of suitable technical options or financial reasons, but of course here there is an advantage of the natural decay, which decrease the activity level of the constructions and equipment. But we will continue with the immediate liquidation, which is now successfully implementing And its transition period after the shutdown includes the preparation of necessary design documentation and infrastructure of the object, as well as planning of the works to be done in the areas of dismantling, decontamination, waste, radioactive waste management, and site remediation. This transmission period is very important because during it, it is possible to define the existing state of the facility by making necessary surveys and also making feasibility studies of the technological of use one or another technologies for different stages of work. During preparation of the decommissioning plan and design documentation, the comprehensive engineering and radiation survey carrying out is a very important stage. It helps to receive the necessary information for all the follow stages. And now we will present to you the digital possibilities of providing such a survey.
The preparatory stage includes important sub-stages: final shutdown of the facility, unloading spent nuclear fuel and nuclear materials, and removing them from the site, bringing the facility into a nuclear-safe condition, removal of working media, routine decontamination of equipment and premises, carrying out a comprehensive engineering and radiation survey, developing a concept for the facility's decommissioning with a feasibility study of decommissioning options and selecting the most appropriate one, developing the facility's decommissioning program, developing the terms of reference for the project in the decommissioning project, preparing a safety analysis report, developing a set of documents to obtain a license for decommissioning, obtaining the license, creating the decommissioning infrastructure, necessary facilities, communication lines, upgrading service systems, etc. Work at this stage results in obtaining a license for decommissioning. The necessary preparation stage for decommissioning is the Comprehensive Engineering and Radiation Survey, CERS. This entails organizational and technical measures necessary to obtain initial data for decommissioning the facility. It consists of an engineering and radiation survey. Within the framework of the first one, the characteristics of the premises, a list of systems, a study of equipment and communications, and information on the actual state of the facility is collected. The radiation survey includes a list of facilities exposed to radioactive contamination, quantity and characteristics of accumulated radioactive material, volume of accumulated radioactive waste in storage facilities, their specific and total activity, radionuclide and chemical composition, gamma radiation dose rates from equipment and radioactive waste storage facilities. On the basis of the CERS, a concept for decommissioning is developed, followed by the decommissioning program and projects. In the future, Rosatom expects a significant increase in the number of facilities to be decommissioned. For a long time, preparations for the decommissioning process and one of its main elements, the Comprehensive Engineering and Radiation Survey, were conducted the old-fashioned way on paper. At present, the technology for creating a digital operating radiation engineering model, DOREM, of the facility is used. The Digital Comprehensive Engineering and Radiation Survey is a process of obtaining data on the engineering and radiation condition of the site. When the collected actual and archived data have a digital format and a systemized structure, this means that the collected data is purposefully grouped around a previously prepared framework, a DOREM, of the site's radiation hazard. As a result, the information the engineering radiation model obtained after the DOREM, which displays the actual configuration and state of the facility, becomes the basis for the digital decommissioning design. Applying DOREM provides a fundamentally new level of preparation of initial data that corresponds to the actual state of the facility, which significantly improves the quality of the results while reducing labor intensity. There are no analogues in Russia's nuclear industry and in the world of applying an integrated approach of decommissioning using digital technologies, laser scanning, spherical panoramic photography, creation of photo tours of all the sites, buildings and structure, integrating the radiation components. This technology can be widely applied not only in implementing decommissioning projects, but also when preparing the decommissioning concept, during the formation of the decommissioning program, and at all stages of the facility's final life cycle. The Siberian Chemical Combine's radiochemical plant is a unique facility. In the past, it processed irradiated standard uranium blocks from industrial uranium graphite reactors. Now it's an operating facility for refining uranium feedstock from the 12 Fuel Company. This is the largest nuclear and radiation hazardous facility, exceeding 5.5 times the volume of the RMBK 1000 unit. Stage 1. A DOREM of the building and structures of the radiochemical plant was created. Work digitizing all available documentation, 11,000 documents, was carried out. Laser scanning and spherical photography was made, including 3,500 photo panoramas and 2,000 scanning points. Using 3D modeling tools, a digital twin of the plant was recreated. The created digital model of the radiochemical plant, in its complexity, content, and scale, is the nuclear industry's first experience in implementing the decommissioning project using digital technology.
So the results of the survey are very relevant in order to determine also the financial side of the decommissioning project. But after this first part of the transmission period, it is based on the results of the survey and the feasibility studies done, the project documentation is developed, and the license is obtained. It is time to go to the next stages of decommissioning, to bring the facility to the rich safety state, with the help of documentation, dismantling methods and instruments, and further to start managing the radioactive waste which are producing during these 2 stages. So now we will further move to the technology, to our experience in dismantling technologies, which were also successfully used at several facilities.
All equipment dismantled in metal structures, except contaminated ones at the decommissioned facility, are reusable material, and after decontamination, they return to general industrial circulation, up to 90% of equipment. Contaminated structures, vessel internals, reactor pressure vessels, etc., and fragments that didn't pass the final radiation control are considered solid radioactive waste of different activity levels, including high-level solid radioactive waste. Various products, including frame structures and long parts, are dismantled and fragmented. A special task involves dismantling, fragmentation, and fragment handling of vessel equipment with wall thickness of up to 300 millimeters, steam generators, reactor vessel, and vessel internals. We perform the following key works: fragmentation of vessel internals, dismantling and fragmentation of the reactor vessel, dismantling production and engineering equipment, dismantling building structure elements, dismantling buildings and structures of the infrastructure and basic facilities if necessary, conversion of facilities. Rosatom has big experience in using conventional fragmentation and dismantling methods. We also have unique solutions that allow dismantling to be done faster and more efficiently compared to standard methods. Plasma cutting, contact cutting, abrasive water jet cutting, oxygen cutting, mechanical cutting, laser cutting.
So as you can see, as conventional methods of fragmentation are used, and as well as the modern and developed during the research and development works. So I would like to show you also the dismantling process, which can be done by the laser instruments.
Based on commercial Litavian fiber lasers, the Joint Stock Company State Research Center of the Russian Federation of Choice Institute for Innovation and Fusion Research created a family of mobile laser systems designed to perform a wide range of operations, including remote laser cutting and fragmentation of equipment as part of nuclear decommissioning. The separation cutting method for spatial metal structures up to 440 millimeters thick allows for fragmenting metal structures at a distance of up to 100 meters and transferring laser radiation through a flexible transport fiber. All the laser systems, equipment, and service staff are located remotely in a clean area, which reduces the dose effect on people and increases time available for continuous work. The system's energy efficiency is up to 35%.
But of course, using these or other dismantling instrument depends also on the facility and equipment itself. For example, when we speak about the conditions of small space and but very thick metal cutting, sometimes the traditional methods also can be successfully used, and I would like to show you the method of steam generation cutting, which was implemented at Rosneft concern.
Rosenergoatom completed work on dismantling and handling the dismantled equipment in the primary circuit of units number 1 and 2 at the Novovoronezh nuclear power plant, including steam generators. The cutting method of steam generators is combined, being a complex production process which includes preparatory work, cutting the steam generator body into large parts mechanically using a circular saw, and thermal methods, plasma cutting, with subsequent fragmentation using bandsaw machines into small fragments to be decontaminated. Cutting and removal of tubes using a hydraulic shear and an angle grinder. Removal of entire collectors with subsequent fragmentation using bandsaw machines. The projects didn't provide for operational openings for the disassembly of equipment, such as a steam generator, and neither the lifting mechanisms in the boxes where the steam generators were located. So it was decided the steam generator should be dismantled in large fragments, because it was difficult to remove it as a whole without destroying physical safety barriers. They were removed from the area where the steam generator was located and further fragmented at special fragmentation units. In addition to steam generators, we're experienced in dismantling and handling other large-size equipment at the Novovoronezh NPP, main circulation pump, pressure condenser, transformer unit, large-size vessel equipment, and pipelines of large diameter.
So if we move further, it is worth saying also about the different methods of decontamination, which is actively used before dismantling and after. Here the variety of methods is also very wide. And among them, there are also as cutting-edge ones and the traditional, but also effective, which have also good competences in use. So if we go to decontamination.
Decontamination means removing radioactive substances from the surfaces of equipment, machinery, and building structures. The main decontamination methods include mechanical, electrochemical, thermal, laser remelting methods, and their combinations. The following works are performed during decontamination: surface decontamination prior to dismantling, decontamination of equipment dismantled and building structure fragments, decontamination of structures of buildings and facilities after dismantling. Rosatom's companies apply more than 10 decontamination methods. Abrasive glass decontamination, cryogenic blasting, metal, shock blasting, metal, pyrometallurgical decontamination for metal, electrochemical decontamination, ultrasonic decontamination, laser decontamination, liquid decontamination for metal, decontamination with concentrated ozone.
And here, let's get acquainted with such an interesting type of decontamination as laser decontamination.
Laser decontamination. The experience of using laser decontamination at the Siberian chemical plant showed its effectiveness in decontaminating objects with complex geometric shapes. The unit is effective for decontaminating alloy steels, non-ferrous metals with an oxide film. It can be used in combination with other decontamination methods, such as liquid decontamination. As part of research and development work, we got good results on decontamination of non-ferrous and stainless metals. The relevance of the method is due to the fact that during decontamination of complex geometric surfaces, it is very difficult to get close. For example, with a grinder, or let's say that after the chemical method of deactivation, not all areas have been deactivated to the required standards. And it is the laser that has the ability to penetrate into hidden surfaces, those of irregular geometry, and by heating, vaporize the radioactive contaminations from those very surfaces, which aren't amenable to other mechanical methods of decontamination.
Of course, all the methods have their own advantages and disadvantages, and it depends on the situation. Then their use will be reasonable. But as for the laser decontamination, it helps, for example, to remove the surface decontamination of the equipment of when the geometry is quite complex. But at the same time, the method has low productivity. At the same time, when we speak about large volumes of metal waste, which often occurs during the decontamination process, it is also worth saying about the one quite universal but rather complicated method of decontamination. At the same time, it is also the method of contaminated metal treatment is the pyrometallurgical contamination.
The listed decontamination methods are only suitable for cleaning radioactive deposits that remain on the surface. But what about deeper contaminants? Pyrometallurgical decontamination is used to decontaminate metal wastes that are characterized by a great variability in morphology and radionuclide composition of contaminants. The metal is fragmented to a convenient size and loaded into an induction smelter. In the inductor's crucible, the metal is melted to a temperature of 1,550 degrees. Various flux additives are added to the melt. The radioactive particle is assimilated in a side layer, which is subsequently removed, and the metal, cleaned to sanitary standards, is poured into molds for subsequent transfer for reuse.
So when we have completed the first two stages of the commissioning process, dismantling and decontamination, we receive the new waste. And here in our virtual tour, we will also show the Rosatom's competence in technologies and equipment for radioactive waste treatment, which of course can be used not only during the decontamination process, but also during the process of radioactive waste management at the existing facilities. And this stage of decommissioning is also very important because the decrease of volume and receive of the waste which are acceptable for further long storage or disposal is the main goal of this stage. So let's start from the from the treatment of solid radioactive waste and the equipment and technologies which are presented there can be implemented for almost all waste streams.
In 2014, Sverdlovsk Chemical Engineering Research Institute supplied a high-pressure press, the so-called superpress, the Novovoronezh MPP-2. This is the first domestic equipment of this class implemented at the Russian nuclear power plant. The high-pressure press is part of the equipment for solid radioactive waste management. It can achieve 10 to 12 times reduction of solid radioactive waste volume through two-step pressing with the use of low-pressure press at the first stage, which reduces the volume of radioactive waste by about 5 times. This pressing is done in standard 200-litre drums, which are then put under a high-pressure press. The briquettes resulting from this processing are loaded by a special manipulator with a stacker into a non-return protected cask, which is then delivered for storage or disposal. This technology makes it possible to significantly increase the waste volume reduction ratio and to use the storage areas for conditioned forms of radioactive waste in a more cost-effective way.
And also, let's have a look at a plasma recycling system.
The system is designed for plasma pyrolytic recycling of solid radioactive waste of medium and low activity and complex morphological composition, containing both combustible and non-combustible components. This method enables high waste volume reduction ratios and to obtain the final product of processing in the form of a fused slag compound that features high mechanical strength and chemical resistance, with a concentration of initial radionuclides of at least 90%. The basis of the radioactive waste plasma recycling system is a shaft-type furnace consisting of a shaft and a smelter, waste loading units, and a molten slag discharge. In the upper part of the smelter, 2 radon-6 direct current arc plasmatron are installed with an electric power of 50 to 150 kilowatts. An identical plasma torch is additionally installed in the pyrolysis gas combustion chamber. The rated power of equipment for general and special purposes is 1,000 kilowatts. The radioactive waste plasma recycling system's productive capacity in terms of solid radioactive waste is 4,800 kilograms a day, subject to the availability of a prepared morphological composition from the resulting solid radioactive waste. The normal operation mode of the shaft furnace is implemented in such a way that most of the radionuclides sublimated from the smelter and carried away by the exhaust pyrolysis gases are captured by adsorption in the pyrolyzed porous mass in the middle section of the shaft, or by the physical condensation of supplements on the waste surface, after which they're sent back to the melting zone. Subject to maintaining a constant level of waste in the furnace shaft, the process mode selected provides a temperature gradient from 1300 to 1400 degrees centigrade in the hearth area. A temperature of plus 250 to 300 degrees centigrade is maintained in the pyrolysis gas outlet zone, which prevents the entrainment of volatile compounds of some radionuclides and heavy metals from the furnace. Maintaining the pyrolysis gas temperature in the shaft's upper section within a range of up to 300 degrees centigrade also ensures explosion safety of the process. As an additional measure to keep the temperature within the required limits, it's possible to irrigate the shaft's upper section with water. Implementing the solid radioactive waste plasma processing is a technologically and economically viable alternative to creating systems for multi-stage treatment of solid radioactive waste based on waste incineration, melting, cementing, pressing, and supercompacting with no need for reconditioning of plasma waste processing products after 30 to 50 years.
So now we have seen some examples of the technologies for solid radioactive waste treatment, but also Here I presented some promising technologies for treatment of the liquid radioactive waste. Let's start from the most common but effective method of cementation.
It's very dangerous to keep liquid radioactive waste without turning it into a solid phase. There's always the possibility of depressurization of the container, and the risk increases many times with prolonged storage. Therefore, conversion into a solid phase is required for safe storage of radioactive waste. The unit for cementation of liquid radioactive waste is developed for cementation of liquid radioactive waste of low and medium specific activity. The operation principle of the unit is quite simple. Cement with additives is fed into the mixer, while the waste from the liquid radioactive waste measuring containers is fed simultaneously with cement. A container is pre-installed under the mixer. The cement mixture with liquid radioactive waste is fed into the container, which is sealed after filling and transported to the repository. The unit is fully remotely controlled. Transport operations with the container are carried out using grippers. The thickness of the container wall enables completely excluding the impact of ionizing radiation on personnel's health. The cement compound has a sufficiently solid structure, and therefore the release of radioactivity is excluded. That elemental base that's poured into the cement compound is either drums or non-return protective casts. It ends up being an additional barrier that prevents radioactive waste from escaping into the environment. It's important to note the process of cementation of liquid radioactive waste is considered to be the most universal and simple method for the binding and fixation of solid and liquid low-level radioactive waste. These cementation units are used at all types of NPPs. The containers are non-returnable and guarantee long-term and environmentally safe storage of radioactive waste.
So when all our waste are already treated and placed into the containers, it is also an important moment to characterize them in order to receive the necessary information for their further life. So now we will also see some aspects of the characterization.
Certification of radioactive waste packages entails measuring the gamma radiation energy spectrum, determining the isotopic composition and specific activity of gamma-emitting radionuclides of solid radioactive waste in packages of various shapes and geometries, measuring the gamma radiation dose rate from packages and surface radioactive contamination of packages' outer walls, in order to document the acceptance criteria for the disposal of radioactive waste packages. The Angarsk Electrolysis Chemical Plant Radiation Safety Service is an accredited testing laboratory. The laboratory equipment can certify radioactive waste packages at all stages of decommissioning and radioactive waste packages obtained as a result of operational activities.
In some cases, during the decommissioning, also very important part of work is remediation. Because of the during decades of the operating, some accidents or something like that can occur, which sometimes leads to creation of large volumes of contaminated soils, and it is very important to implement this work in a safe and effective manner. So here I'd like to present you our technologies of soil sorting according to the radiation characteristics.
The Fremen's unit, developed by Nuclear Technologies, a member of the TFEL fuel company, is designed to separate radiation-contaminated bulk materials by flow gamma spectromic measurements on a conveyor, followed by automatic sorting according to specified limit values based on the radionuclide vector. The technology enables separating material into three classes, according to the total specific activity, depending on the measurements results, to separate clean material from contaminated, and to separate contaminated material into two streams for further treatment according to the level of contamination. The key advantages of the premise unit are high throughput, process automation, which virtually eliminates the human factor, and mobility. In addition, the system allows for characterizing various types of bulk materials, soils, sand, slag, and even crushed concrete and bricks.
So when our site is when our decommissioning work is almost done, it is also a very necessary question of the safety disposal of the radioactive waste which we receive during these stages. And final isolation is successfully implemented for low and intermediate level waste, and now we will have a look at one of our disposal facilities.
All options for a near-surface disposal site for radioactive waste are based on a system of passive safety barriers to prevent the migration of radionuclides into the biosphere or a significant slowdown of this process. For this purpose, we use various combinations of artificial and natural barriers. The parameters of barriers used can differ significantly depending on the project. There are at least 3 different concepts for such disposal sites, depending on their location relative to the Earth's surface. The near-surface disposal site in Novoural was the first one put into operation in Russia. This site is designed to dispose of short-lived and low-active radioactive waste. The disposal site in Novoural is based on a multi-barrier principle. 6 barriers prevent the spread of radionuclides from 3rd and 4th class radioactive waste, mainly overalls, ventilation system filters, and plastics containing uranium isotopes. The first barrier is waste packaging. At first, waste is put in 200-litre metal drums, which are placed 4 at a time into special iron casks with a wall thickness of 12 centimetres. That is, the casket body is a second safety barrier. Then we place these casks in our disposal site, and we fill the space between the casks with barrier materials, special clays. This is the 3rd safety barrier. The 4th safety barrier is the 70-centimetre walls of the storage itself, made of high-quality concrete. The 5th barrier is waterproofing materials which are laid around the site. And the 6th safety barrier is the geological formation, in which this disposal site is located. These are the steps that prevent radioactive substances present in the waste from escaping into the environment.
So we have shown you some, but of course not all the technologies and products which we have, and it is necessary to say that the commissioning of the first generation nuclear facility is, of course, a strategic challenge for the whole nuclear industry in order to meet the United Nations goals of sustainable development, but also for Rosatom, for 12 company, it is not only just a business, but it is also the responsibility for the future generations. Of course, all these cannot be done without the high quality staff which is involved in all the processes. The companies in Rosatom create the favorable environment for the effective work where people can realize themselves as specialists, and also it is obvious that safe, efficient, and cost-effective approaches to decommissioning is the key for the successful development of the whole nuclear industry. So thank you very much for your attention. We are always open for the dialogue and the questions which can be, and I'm very glad that I had this opportunity to present you this virtual journey. Thank you very much. So, are there any questions? Yes, please.
you can use.
Will this virtual tour as material will be given to us for from this seminar? Let's say we can have this virtual tour as a material, because I want to see some specific issues about the graphite decommissioning, because in Greece we have, sorry.
Yes, of course. Unfortunately, we haven't an opportunity to show all this, all the movies we have about the graphite tractors, decommissioning, and yes, and the virtual tour is will be acceptable for you after that. Yeah, as a video. Thank you very much.
So now we will have short presentations from the participants. We will need some time to copy the presentation that you already sent. If you have your presentation with on USB stick, we can copy it directly here. If not, you can send it to the group chat and we can copy from the chat. Okay, so it takes something like 10 minutes for us, so you can join the coffee break at the moment, okay? So, okay, we will start with the presentations. Let's go just by the name of the presentation. So we will start with our Greece colleagues. Yeah, okay.
Thank you, Vladimir. Yeah. I didn't prepare a certain presentation for this school, but I can talk to you about a recent activity that we have. I'm from the Aristotle University of Thessaloniki in North Greece. Aristotle was a philosopher from North Greece, so that's why this name in the university. And especially we have a nuclear technology laboratory there, which mostly make some research in environmental radioactivity. I'm Ioannis Kaissas, assistant professor in this nuclear technology laboratory. The other two professors are the emeritus professor Alexandros Klouvas and Stelios Xanthos, former working in our laboratory, but now he's in another university. So our laboratory make recently a study about the cesium migration in the different depths of the soil in Greece. Let's say we have some radioactivity on the soil produced by the Chernobyl accident back in 1986. So it was a huge amount of radioactivity released into the atmosphere, and some of it came also in Greece. We have a radiological map of Greece made in the April of 1995, and we measure some radionuclides, including cesium-137 and 134 back then, because nowadays the 134 is decayed completely, and also the iodine 131. So we have some measurements back then, and we make the conclusion that practically all the cesium-137 in the soil due to the Chernobyl accident in Greece came from the Chernobyl accident and not from the nuclear weapon tests that are made around the globe. That has to do with the measurements of the ratio between the cesium-137 and 134. The measurements of the different concentration of cesium in different depths of soil have been made in an undisturbed soil which were located near the airport of Thessaloniki, and it's the university agricultural farm, let's say, of the university. And we know that this particular place there didn't disturb, didn't cultivate it or make something about construction on this soil. So we have it undistributed from the Chernobyl accident in 1986 and since now. So we take our sampling with a rod, a tube, and we take these sampling every 5 centimeters of soil of different depth. We make some drying of this sampling to get out to get rid of the moisture. We make it let's say more uniform and measure it in a high purity germanium detector. And we find out that in different layers in 1987 and in 2023, we have different concentrations of cesium. And one can see here that the concentrations back then in 1987 were more high in the first layer from 0 to 5 centimeters. And nowadays, the cesium mitigate in lower depths. And now the concentration of 0 to 5 centimeters and 5 to 10 centimeters are a little bit the same. It's 92 and 89. So I don't want to take much of the time, just to show you that we develop a mathematical compartment model to explain this mitigation of cesium to deeper depths of soil. And the compartment model, this mathematical model, is quite in agreement with the measurements, with experimental measurements. Let's say for a result, and I will finish with that, that we find out that the cesium mitigate every year 1.2 millimeters downwards in the soil, okay? And just to show you a relevant a paper that we published recently, you can find out more details on this. Thank you for your attention.
So next one.
Greetings, dear colleagues. I'm Maliborsky Artem, and I'm the lecturer at Belarusian Radiation Chemistry and Chemical Pharmaceutical Technology Department of Belarusian State University. Here you can see my wonderful colleagues, which are a bit separated, the younger part, and on your left, my right, and the older part on your right. You can see it's quite a small, I think, company of people who teaches students at Belarusian State University in the disciplines of radiation chemistry, radiochemistry, and nuclear chemistry. Our department has an interesting and quite old history. It was founded in 1968 by Evgeny Petryaev, but it's like a scientific approach field. It existed even before. It was only founded in 1968. And it was mainly devoted to the radiation chemistry of water solutions. After 1986 and Chernobyl disaster, our university and our department in particular was tasked to convey the research of contaminated earth and other samples from Chernobyl. And so the radiation laboratory was founded and worked firmly till nowadays as an independent laboratory under our department. So, about some information about myself. I graduated from Belarusian State University in 2019, finished my master's degree a year later, and still then work on my PhD, which is devoted to radiation peroxide-induced radical transformation involving different hydroxylic compounds in aqueous and organic solutions, which is our primary field of science. But why am I here in School of Radiation Chemistry? As I said, our department has a very close relations with radiation chemistry. And when our country decided to build a nuclear power plant, there was a task from the government to start teaching the new generation of chemists that will work there. And we put this task to action. Therefore, there are a lot of courses that we teach that includes radiation chemistry, nuclear waste management, which are taught not only to the bachelor degree students, but to the master degree students. And we will need to accumulate, assimilate, and to process this knowledge to students. And to do this, we need to find new, of course, and relevant information, which is presented here, of course. And the main goal of our task is to inform and interest the students into the field of radiation chemistry, like radiation regulation, monitoring, so that they will be quite proficient workers when they will be hired in government companies or they will work in nuclear power station. If you are interested, it's like a small diagram what we're doing in our department. We're trying to model the processes which involve different radicals in our organism by irradiating the sufficient models, which can be used as simple models like ethanol, propandiol, propandiol 1, 2, or others. And it can be quite a complicated models like lipids or cardiolipin or we're doing phosphatidylcholine. These lipids are used to model solutions, and we irradiate them basically and watch the products. So thank you for attention.
Thank you. Let me introduce myself. My name Renaldi Bernardo Saragi. You can call me Ray. I'm from Indonesia, and now I'm the sixth semester student in Polytechnic Institute of Nuclear Technology of Indonesia. And now my specification is decommissioning project, and my project now is to carry out the final research of the strategy decommissioning 2000 Bandung research reactor and waste treatment. And unfortunately, I'm not supplement the document for the progress of my final research of decommissioning in 2000 Bandung research reactor, but in the brief, 3000 Bandung is our first research reactor in Indonesia, and now is the oldest research reactor. The age is almost 60 years, and yeah, this reactor building in our first president era, and I'm working this project with MCNP program with Origin but now for the specific, my material is only about the graphite flux neutron, and this flux neutron be calculate and be measured with the characterization and the data of the configuration, the core be processed with MCNP and convert in origin program. I think this is the first, and yeah, enough for me. Thank you.
Thank you for the chance. Let me introduce myself. Uh, uh, Before that, I would like to say sorry because my presentation is shorter than the other participant. But I can tell it with long, so you can enjoy the the all of thing about me. Okay, my name is Rido, only Rido. Just one word. I born at Semichirim, 5 April 2002. My address, Medan, North Sumatra in Indonesia. I am a student at Polytechnic Institute of Nuclear Technology, majoring nuclear chemical engineering. Polytechnic Institute of Nuclear Technology is a institute in Indonesia, and I am majoring in nuclear chemical engineering, which is studying about nuclear and chemical engineering. But the real translation about my major is nuclear technochemistry. But I write this at this presentation is nuclear chemical engineering, which is studying about some of nuclear technique and science and chemical engineering as a pure chemical engineering on the other campus. My hobby is enjoying the beauty of nature, because the nature make me relax, and if I relax, I can think. Uh, I I can think of with good, and then I do not have any research yet, but now I am interested in computational fluid dynamics, especially if I can applicating it to the nuclear reactor, for example, and the other. So I think that's all from me. Thank you.
So, first of all, good evening to everyone. First of all, I would like to thank our great organizers, the Rosatom and Moscow State University, to conducting a really interesting international school about radio chemistry, main topically treatment of waste management. Thank you. Thank you. So, directly into my introduction. So, my name is Sri Vignesh Punaram, and I am in currently fourth year medical student studying in Russia, Moscow, in MEFI. So, generally, my what's it? My academic excellencies over in my higher schooling and colleges have been receiving the academic excellencies from past 3 years in higher schooling, and in my school life also I was been awarded with the academic excellency scorings, and actually even I was involved in sports which is known as kabaddi in India. Yeah. So generally each persons have so many hobbies. So generally I'm going to share those hobbies which I have reached milestone. So first hobbies which I have reached milestone was writing poem, and I was awarded as first prize in one of the Indian famous magazine called as Jellyfish Movement. And international recognition of these milestones was like 2 years back. I was like my poem was even published in one of the Russian magazines, which is published by Mefi. So generally I am a bit learning into psychology, and recently I have started getting nuclear medicinal professional from the IAEA, which is like a collection of all short courses into one big course. So you might think now, like, why a medical student coming into the radiochemistry steam listening about waste management about radionuclides. So generally to this point I would start from a short history where I recently met a patient with radionuclide treatment to the cancer, and the patient was explaining me about how the doctor explained him, so how this radionuclide will go to the cancer cell will shrink, die, and the patient cures from the cancer. And from that point I got bit curious about how this radionuclide is being treated in medical line. So even in last year's winter schooling I was happy to be here and learn about radionuclide in medicinal use. And this summer schooling about radionuclide waste management, because one of my doctors told, like, with all radionuclide use there is a short wastage which is going to be the result of any radionuclide usage. So then I got a bit like even a small use can cause so much wastage, and how in a big scale like in factory uses how this waste is being used, and how it is managed in an industrial scale. So thank you.
So I think that we don't have any presentations, but we can just put this mic through the lines, through the people, and listen their stories. Let's start with you.
Can we go together?
Yes, you can.
Здесь?
So, hello everyone. We are students from Republic of Belarus, and we are from Belarusian State University. Our major is chemistry of the high energy, and now we want to tell you about ourselves. In first, my name is Alexander Nosko.
My name is Kirill Tsikhamirov.
I'm Alexey Yakas.
I'm Nadezhda Zanevskaya.
And I'm Ruski Mikhail.
So we are in Moscow not the first time. We also were here in spring of on 2023, and we listened a lection course about radioactive basics, about ecology, radioactive ecology, about Chernobyl disaster. And our lecturers was the employees from company Doza. Also, we was in Tomsk in this spring. We saw the research reactor. We listened the lecture course from Tomsk Polytech. And also we listened course from distance course from Czech Technique University. They tell us about their own research reactor. We saw lectures, we saw how it works. We listened how works the reactor kinetics and so on. Also, we are planning our travel in St. Petersburg to visit the Leningradsky NPP. So.
And I take part in a international school on ecology. It's get more useful knowledge for me, and I think this school gets some news knowledge where deeply to understand nuclear waste management and other terms of.
Yeah, in our university, we studying many courses like radiochemistry, like nuclear chemistry, nuclear physics, and more else. And we have some knowledge for this school, and we.
So we decided to come here to deepen our knowledge in field of nuclear chemistry and waste management. So our country recently started the second power unit, and we believe that the knowledge we will gain here will help us in the future, in our future work.
Thank you for attention.
So the next one, Jules. You can also go together.
Hello, everyone. We are also from the same university. My name is Diane Nyakiziman.
Name is Susan Version.
We are from Rwanda, in Africa. We are graduate. We graduated this month in Mefi University at Obelisk City in nuclear physics and technology, like applicable in life science. I think that's all. Thank you.
So next, please. Yeah, don't worry.
So good day to one and all. This is myself, Balraman Ganesan Sri Samandeshwari. I just completed my second year course in general medicine in Mefi University. I am from Chennai, which is a city from the southern part of India. I came from a place where it is more of colorful and activeness, but I expect that it would not be able to possible over here. But it all got just changed because I had more opportunities to explore more, to learn more, and to live more. So that's why I just love to explore many things. This is the one of the opportunities I got. Not one of the opportunities, it's a big opportunity actually. So I like to learn from many of the persons over here because your guys are all more experienced and are more knowledge. So I'm here to build up myself to gain knowledge.
Hello everyone, I'm Nila Rafila. These are my colleagues from MEFI, and we are doing our medicine courses. So actually, since we're at MEFI, we had a chance to have a few semesters about radiopharmaceuticals, applications of radioactive compounds in medicine. And I think it's like really, really helppful, really useful. And to establish such practices in different countries, we need production of radiopharmaceuticals, active compounds via power plants or etc. And to establish such places, we do need to have a plan, a management for radioactive waste disposal. So more awareness about this topic, I think it's really informative because it's really useful. You know, there are multiple practical uses for radioactive compounds in medicine. So I feel like getting a better understanding of the basics can, help me in my future. Perhaps I might go into nuclear medicine, wherein we do need to know about nuclear production and management of such compounds.
Hello everyone, my name is Sri Shweta Vinod Kumar. I am from India, Chennai. I am also studying in MEFI Moscow campus, and we are also all from general medicine. And we have been studying some radiopharmaceuticals and nuclear medicine in our courses. To get more knowledge, we came here. Thank you.
Yeah.
Hello, dear college. My name is Muhammad Abdel Nasser. I'm from Egypt. I've graduated in the previous year from Tomsk Polytechnic University, field of nuclear power plant engineering, design, and operation. Already studied the same thing. Actually, I started my university in Egypt, at the Egyptian Russian University. I studied there 3 years. After that, I came to Tomsk to continue my study. I studied 2.5 years. Then I graduated, and now I'm studying nuclear science and technology at Tomsk Polytechnic University also. And I'm glad that I came here to this summer school to get some extra knowledge about radiochemistry and management and radioactive waste of management. Thank you.
Thank you.
Hello everyone, my name is Omar. I'm from Egypt. I finished nuclear power plant design and operation specialist in Tomsk Polytechnic University. Also finished master degree. My research topic it was design the second circuit of VVR reactors, design for configuration of the second circuit. I take a diploma for this, and now I'm PhD student in Tomsk Polytechnic University. Thank you.
Hello, dear participants and organizers. My self-introduction will be short. Okay, my name is Valeria, and I'm a first-year master's student at the chemistry department of Belarusian State University. My master's program is nuclear and radiation safety, and my field of interest is natural radioactivity and radiological monitoring, in particular radon in environmental objects. So I did an internship at the Department of Nuclear and Radiation Safety, Belarusian Nuclear Control Authority, under the radiation waste management team. And I'm extremely grateful for this opportunity to expand my knowledge on this field. And I'm looking forward to working with all of you. Thank you.
Hello and nice to meet you all. I'm Evgeny Usik. I'm working in Gosatomnadzor. It's a regulator of the nuclear and radiation safety in the Republic of Belarus, ex-student of BSU. So, guys, a little bit early. What I'm doing in Gosatomnadzor, mostly we are contacting with other ministries and companies in which can be produced radioactive waste. For example, we are starting in building of a national repository of radioactive waste on the territory of the Republic of Belarus. So we are dealing and safety forcing them to walk in the sphere of legacy in the Republic of Belarus. Thank you.
So, nice to meet you all of you. My name is Valeria Dmitrieva. I also work in Department of Nuclear and Radiation Safety in the Ministry of Emergency Situation, Republic of Belarus. In my country, it's a regulatory body. And I also graduated from the Belarusian State University Chemistry Department, like a lot of people in this room. My main duties is supervision over radioactive waste management and spent nuclear materials. In the so different object in Republic of Belarus, from some medical object facilities, hospitals, or something like this, to our NPPs. Also, my work includes development of regulatory framework in my country and analysis of documents which justify radiation and nuclear safety. Also, during my work, I take a part in development of radioactive waste and nuclear material infrastructure in my country, because Belarus has a big way from Chernobyl disaster to our first nuclear power plant. And right now, I'm working like as EIA expert and the guide of development of infrastructure of radioactive waste management. Thank you for your attention. Oh, no. One more. Sorry, I forgot. I want to say thank you, the organizers, for your brilliant work, and I really appreciate the opportunities to be here.
Hello, everyone. Good evening. I'm Dilum. I'm from Sri Lanka. I'm a nuclear power engineering and thermal physics student. And right now, currently, I'm working with the project from Rosatom. It's called Russian Nuclear Ambassadors. And I'm the co-leader of the outreach and cooperation. And here I'm with my few colleagues from the project, also Miga and Omar. And also, yeah, and I'm also working as advocate for the United Nations SDG goals representing my country, Sri Lanka. And also part-time, I'm doing volunteer work with Rotary International. Yeah, that's it. Thank you.
Thank you.
So hello everyone, my name is Miga. I came from Mongolia and I came to Moscow like 9 years ago, and I finished my bachelor's and master's degree in Moscow Power Engineering Institute. And now I'm doing my PhD on also same department, and I'm an electrical system engineer, work in a Russian project company as a constructor engineer. And also I'm an assistant teacher in my department. Yeah, and as Dylan said, I'm an ambassador, so I am participating in so many different like events like this summer school and Obnisk New, where there's so many events actually we are participating as an ambassador. So I am so glad to be here with you guys, and I hope that in this week I mean, it's more than we can wait, right? So we will have some good times and enjoy. So thank you so much. Yeah.
Thank you. I think we heard all participants. Yeah. Okay, so now we will have a good time. At 6 o'clock, we have booked a nice dinner not far away from here. I think that so we can start in 15 minutes, let's say, in 6:35. We will meet each other on the first floor, and we will go together to the restaurant. Okay, so it's just 10-15 minutes by walk. Okay, so see you all in 15 minutes downstairs. Okay.